used a widget that we have. So
we're live now.
okay. We have people already logging on to chat. Norm Hughes says, good afternoon, everyone. Looking forward to an awesome presentation.
Optimistic.
Dr. Bell Burnell, I'd like to introduce you to Maynard Pittendray. He's our executive director, executive secretary, rather.
Hello.
Hello, nice to meet you.
Thank you for the invitation to be with you.
We're looking forward to it. Chuck and Terry have done a great job so far with the leadership and the organization. And it's not easy. And I know.
Yeah. It's a very ambitious project too. You know,
Maynard ran our 2019 convention, which involved a cruise to the Bahamas. And that was quite an undertaking.
yes.
There's nothing better than to have a cruise to the Bahamas during hurricane season when the seas are calm.
He said I had a bit of a nightmare about this convention right before it started. I couldn't get home in time from something, and Maynard said he had a similar experience. And I said, was it something like the Poseidon Adventure?
As I recall, we missed the hurricane season about 1 week or something like that.
Yeah, we did.
Well, we didn't miss the pandemic by but a few months.
That's right.
Did you miss it like you wish that you were there with it, or?
Well, no. I mean, a lot of people got stuck on cruise ships. A lot of people got stuck on cruise ships.
Yeah.
Oh my goodness.
In March and April.
Yeah, that must have been tough.
It's horrible.
That would be awful.
Mm.
My sister and I were on that cruise, and she had mentioned, well, I sure am glad we were back before all of that started happening.
Yeah.
Don, this is Dr. Bell Burnell is with us. This is Don Nab, who handled our website for the convention.
Ah, hello, good evening. Oh, sorry, it's not evening with you.
I'm outside in the garden.
Hello, everybody.
Jackie.
Hey, Jackie.
Hello, Jackie.
Hey, Dovid.
Hi.
For all of you that have Facebook pages, if you could share this to your friends and to any groups that you belong to that you think would be interested, helps the educational outreach part of this.
Dr. Bell Burnell, Jackie Beischer is past secretary and treasurer of the league, and she's the treasurer of our trust fund as well.
Wow, great work.
Thank you.
Mm.
And Don Mackholtz is joining us, I think. Comet Discoverer, Peltier Award winner.
Great.
Okay,
Yep, I'm here.
welcome.
Hi, Don. It's good to see you again since yesterday.
Hi, Dave.
Don Nab, you look like you're out doing gardening.
I am gonna listen to the talks and do some gardening. Yeah, just to figure out how to mute my iPhone. That's all. I'll figure it out.
I think Dr. Bell Burnell does some of that, so she'll probably understand.
Yep, it's a beautiful day.
Remember, everyone, just as a reminder, to mute yourselves while we have speakers, so we don't have any background noise.
Well, hello, everybody. This is Scott Roberts from Explore Scientific and the Explore Alliance. And it is my pleasure to open the third day of the 2021 ALCon event, the Astronomical League Convention, which is being held virtually this year. So wherever you are in the world, you're going to see an amazing lineup of speakers and see thousands of dollars of door prizes being given away. I present these programs. We present programs almost daily, but this is a very, very special one and something that the league officers have been planning for months. And so I think you'll be very impressed with what they've already done, which you can watch on rerun on YouTube and Facebook. You can go to their Facebook Astronomical League page to watch them. You know, if you're watching now and you have questions, please ask them. We'll ask the presenters towards the end of their talks your questions. But this is really a nice platform because you're really being interactive with some of the top astronomers and scientists from around the world. So one of the people that has been on virtually every presentation that Explore Scientific has given is Dr. David Levy. David is with us now. He has written over 20 books on astronomy, as well as books about astronomers. And his recent book is called A Night Watchman's Journey. David is poetic. He loves searching the sky for comets, and he's done it all of his life, and he continues to do it and inspire all of us. So, David, I'm going to turn it over to you.
Thank you so much, Scott. And today, the final day of the Astronomical League convention. We look forward to holding an in-person one next year in Albuquerque. And since today our major talk will be Dr. Bell Burnell, that is really going to talk about major events in astronomical history, the discovery of the pulsars. So I thought for my quotation today, I would also do a historical quotation about Halley's Comet. It is from someone whom you all know and who is also very seminal with the Astronomical League, Leslie Peltier. And he wrote in Starlight Nights, "Within historic times, 28 visits by Halley's Comet have been recorded. On an early trip, it witnessed the defeat of Attila's Huns in AD 451. It arrived in time to preside over the Norman conquest in 1066. In the year 1456, the menacing appearance of the comet so alarmed Pope Calixtus that he decreed several days of prayer, and he established the midday Angelus. And with a great clanging of bells, he then besought the comet to visit its wrath solely on the invading Turks. In 1607, it was watched by both Shakespeare and Kepler. And I like to think that it was also seen by Captain John Smith and Pocahontas in the frontier skies of Jamestown. On his following trip around in 1682, the comet was observed by Halley himself, who probed into its periodic past and bequeathed to it an honored name that it can bear with pride throughout the solar system. By 1835, when it returned, affairs of Earth had speeded up. Many a canal boat traveler looking down could see the comet glowing on the surface of his highway. Humanity himself had taken to the skies when the comet appeared in 1910, for he was making fledgling flights of perhaps 100 miles. In 1986, our historic visitor was visited in turn, for in that year, a spacecraft from the Earth, Giotto, held a rendezvous with Halley's Comet out in space. Who would venture to foretell the wonders and achievements which the comet will witness in that distant year of 2061? Or will humanity himself prove periodic? Will the Huns be back again? And now I give you Terry Mann. Thank you.
Thank you, David. That was absolutely beautiful. I love that book. That's one of my favorites. So for right now, I think I will turn it over to Chuck Allen.
Okay, thank you, Terry. I'd like to display, first of all, just a reminder to everyone that we are live streaming this event on our YouTube channel, and it is available with closed captions. And the link is available on our convention website at alconvirtual.org. So I'll leave this up for just a second or two. Okay. I have a deck of cards here. It's called Legends of Science. It was created by a preeminent scientist in the United States. And in this deck of cards, there are 25 scientists who are recognized. 10 are legends of the past, and 15 are current legends of science. Just 25 people. A couple of them are people you've heard of: Isaac Newton, Charles Darwin, Albert Einstein. And one of them is Jocelyn Bell. And our guest tonight is Dr. Jocelyn Bell Burnell. She was born in Northern Ireland. And when she was little, she used to go to a planetarium that her father, an architect, had designed. And the staff there encouraged her to pursue astronomy. And she did so. She received a Bachelor of Science degree in physics from the University of Glasgow, and then went and received her PhD at the University of Cambridge in 1969. And while pursuing that PhD, 2 years before, in 1967, she was reviewing some charts taken by the Interplanetary Scintillating Array. And she detected a little scruff on one of those charts that she'll tell you about, I'm sure. And she referred to this little pulsing signal as little green men, or somebody did shortly after this. And it was later determined to be pulsar B1919 plus 21. The first discovered pulsar, rotating neutron star. This research resulted in the award of a Nobel Prize to her supervisor in her PhD program, a source of enduring controversy, which we won't get into here. But suffice it to say that the fame that's associated with the discovery of pulsars has fallen to her and no one else. She is a visiting professor at Oxford University and chancellor of the University of Dundee. She won the 2018 Breakthrough Prize, a $3 million prize that she donated, and I think it's administered by the Institute of Physics, for the benefit of women and minorities and refugees in pursuing research in physics. That tells you the kind of person she is. She's a past president of the Royal Astronomical Society, and she's won the RAS's Herschel and Gold medals. She is a fellow of the Royal Astronomical Society. She is also the first president of the Royal Society of Edinburgh as well. And she has been dubbed Dame Commander of the Order of the British Empire as well. She has raised a son. She loves gardening and choral music and poetry. And she is a very active Quaker as well. It is my intense honor and the honor of all of us here at the Astronomical League to welcome you, Dr. Bell Burnell, and I'll turn the program over to you.
Thank you very much for that very generous introduction. Just let me share a screen. Right, is my screen visible?
Yes.
It is.
Brilliant. And I will do subtitles because I have a curious accent by your standards. Thank you very much for that very generous introduction. And thank you also for the opportunity to be with you at this very big ALCon meeting. I'm amazed at the organization that must have gone into such a huge meeting. So I was asked to talk a bit about the discovery of pulsars in context. So that's going to include some geography and some history and quite a lot of astronomy. I'll start with an introduction to radio astronomy, say a bit about quasars, quasi-stellar radio sources, talk a bit about being in Cambridge, UK, that is, and the discovery of pulsars, and a bit about what pulsars are, what we understand them to be these days. So this wonderful photograph is of the big radio telescope at Jodrell Bank in the north of England, with a lovely red setting sun as well. This particular radio telescope has recently been made a World Heritage Site, which is fantastic news for radio astronomy, although probably a big headache for the University of Manchester that owns and has to look after the radio telescope and keep it going. Radio astronomy started at the end of the Second World War, the mid-1940s. It started when people who had worked in radar during the war acquired by various means some of the radar equipment and took it back to the universities that they were associated with. They were particularly interested in the radar receiving equipment. The transmitters they did not want and did not use. During the war, it had been discovered that the sun could occasionally emit radio waves. I don't know whether the story is true, but I was told that the Japanese were very puzzled by something that blocked their radar from time to time. It was low in the east in the morning, high in the south in the middle of the day, and low in the west in the evening. And they could not work out what it could possibly be because of the way it was moving. I suspect the Japanese are a lot cleverer than that, so the story may be apocryphal. But it's been known for quite a while that the sun can produce radio waves. And the thinking of the radar astronomers turned radar technicians turning radio astronomers was, if the sun can give us radio waves, maybe some of the other stars can as well. So the field was developed by ex-radar boffins. That may be a British word, it means sort of experts. And when they turned their rather primitive radio receiving equipment to the sky, they found a lot of relatively strong radio emitting objects. They were clearly part of the sky because they moved round at the same rate as all the stars. And when they managed to position some of them, they'd say to their optical colleagues, what is there at a particular position amongst the constellations? Because whatever it is, it gives quite strong radio waves. And the optical astronomers would go look at that position and say, well, there's something that looks a bit like a star, but it's not like any kind of star that we've ever seen before. And so they became known as quasi-stellar or quasi-stellar radio sources, quasars for short. There was a significant development when Martin Schmidt, working in California, I think he was originally Dutch, but I suspect he'd been naturalized American by then. He got some spectra of one of these peculiar objects, and he was puzzling over it. He had real trouble making sense of it. There was what looked like a hydrogen spectrum, but it was in the wrong part of the spectrum. It was way, way to the red end of the spectrum from where it should be. And he didn't know any other chemical element that had a spectrum like that. And as he puzzled, he thought, well, maybe it is a hydrogen spectrum with a redshift. And he worked out that the redshift, delta lambda over lambda, was 0.16. This was alarming because that redshift implied a large distance. They already knew that the universe was expanding and that the more distant objects were expanding, moving away faster, and had larger redshifts. So this redshift implied that this quasi-stellar thing was about 3 billion light years away. And yet, as he said, it was bright, like a million suns. A colleague, Jesse Greenstein, had an office along the hall, and he went to talk to Jesse. Jesse at that point was trying to write a paper saying why the object that he looked at was made of tellurium, because tellurium was the only element that had a spectrum even approximately like what he was observing. And Martin said to Jesse, could it be hydrogen redshifted? And Jesse tried that and found that indeed it was, with a redshift even larger than Martin's, 0.37 against 0.16. So Jesse's object was even further out in the universe than Martin's, definitely way, way, way beyond the galaxy in a really distant part of the universe. Apparently, Martin went home that evening and said to his wife, something terrible happened at the office today. And he wasn't joking. He was genuinely very shaken by what his spectrum was telling him and what Jesse's spectrum was telling him. So now just a little bit about my path, because you asked for some context. So here comes the context in the form of geography. As was said in the introduction, I started life in Northern Ireland at number 1. I had my secondary schooling at a girls' boarding school in York at number 2. I then went to Glasgow University to do my Bachelor of Science degree. I had decided before I left high school, that I wanted to be a radio astronomer. And doing a physics degree seemed the right thing, good start. And if I failed to be a radio astronomer, I could doubtless get a good job with a physics degree. But when I finished my physics degree, I failed to get a place at Manchester at Jodrell Bank. I thought I was probably going to have to go to Australia, to Sydney, to do my PhD. But the academic year in Australia doesn't start till January, February. So I had some months in hand. And just in case, I put an application into the University of Cambridge, which is at number 4, way, way south. Now note the shading in this map. I have been in mountainous areas of the country until I go to Cambridge, which is in low-lying, dead, flat countryside. Totally different. And the landscape was alien, and so was the place, to be absolutely honest. Of course, in the United States, you're egalitarian. You don't have any geographic gradients, do you? But as perceived by people in the south of England, people who live in those brown speckled areas to the north and west, it wouldn't be said in so many words, but they're felt to be uncouth savages, whereas the southeast of England is ultimate civilization. So here am I, an uncouth savage, trying to make my way in a place that's ultimate civilization, Cambridge. I go there and I'm overawed. There are very few women. There weren't places for many women in Cambridge at that time. There's a lot of very confident young men who've been at fee-paying schools who are absolutely convinced of their own brilliance, absolutely convinced of their right to be there. And I'm from the north and west, and I'm female, and I'm not sure I should be there at all. I think they've made a mistake in admitting me. I think they're going to discover their mistake and throw me out. This is called imposter syndrome, and I'm sure it happens at the prestigious universities in the United States as well. There can be people who are overawed by the prestige of the place and quite convinced that the university has made a mistake admitting them, is probably going to throw them out. And in bad cases, the student says, I'd better leave before they throw me out. And if we don't watch out in Oxford, where I am now, or in Cambridge, where I was, you'll find that a new student has gone back home within the first week of the first academic year starting. So we work quite hard to try and trap those students, to give them confidence and help them to stay on. But imposter syndrome wasn't recognized or named way back then in the 1960s. But now that I know what it is, I recognize it's what I felt. Discomfort was increased when, in the first week, I got given a set of tools. All new radio astronomy graduate students, except for any curious guys called theoreticians, were given a set of tools. This is my set of tools, and I still have them. And you'll see they are not microelectronics tools. These are full-size wire working tools, because I'm going to do a lot of wire working. I spent the first 2 years as one of a group of about 6 people building a radio telescope. My responsibility was all the cables, the connectors, the transformers. It was a huge radio telescope, covered an area equivalent to 57 tennis courts, and was really relatively cheap, £12,000. Now, £12,000 back then, of course, was worth a lot more than it is today, but it was relatively cheap because it was built with student labor. The photograph is taken near the end of the construction. Our technician, Don Rolfe, on the left, and myself wrapped up warm against the cold, checking the impedance of some air-spaced cables, or at least checking that the connectors are on properly by checking the impedance. These air-spaced cables could not be coiled up and taken indoors, so through a Cambridge winter, I sat either in the little red hut behind me or in the little red hut, I've lost the cursor, back there, which was where the other end of the cables were. And I sat in these huts putting these sockets, plugs and sockets on the cables. And we're now testing them with a slotted waveguide, checking the impedance. So I got very fit and very brown, and occasionally somebody would say to me, have you been on a skiing holiday? Where did you go? Comment not appreciated. It was extremely cold, very hard work. But we built a radio telescope, and this is the finished article. Most prominent are the wooden posts. They are only there to keep the wires out of the wet grass, because wet grass is an electrical shock. We have antennae, here's the cursor, antennae running like this. The signal's brought down by these curving copper wires, joins what we called a tram line, which went away off, joined other tram lines somewhere over here, got converted into coaxial cable and went half a mile back to the laboratory. Working at radio frequency, it's an array of dipoles, half-wave dipoles, over 2,000 of them. And the receivers used vacuum tubes. I'd used transistors in my undergraduate research project, but the radio astronomer said, whoa, transistors are unreliable. Whoa, transistors are noisy. We use vacuum tubes. And they did. They ultimately changed the transistors, but not for quite a few years more. Now, this particular project was to find more quasars, and that's what the telescope was built for. At the time I arrived on the scene, there were probably only about 20 quasars known, And that's not really a very large sample. The project was to find more and have an attempt at measuring their angular diameter, their size. And it involved repeated mapping of the sky. Because quasars have very small angular diameter, they twinkled, technical name, interplanetary scintillation. And because we needed to pick up this twinkling, we had to work with a very short time constant, a very short integration time of 1/10 of a second. Short integration times put up the noise, and to improve the signal to noise, we had to build this very large antenna to pick up lots of signal. Having spent 2 years building the radio telescope, I spent 6 months observing with it and found about 180 more quasars. So I got the number of quasars up from 20 to 200. And that was my main thesis project. And my thesis advisor was Tony Hewish. I want to explain why it is that quasars do this twinkling or interplanetary scintillation. Way up at the top of the picture, there's a quasar. It's actually way off the screen, way off your screen, up through your ceiling, way up in the sky. It's very distant. And we have a radio telescope on the Earth, and the radio signal from the quasar comes through the solar wind to the Earth. The solar wind is not smooth. There are density irregularities, electron density irregularities, a bit like clouds. And as a radio wave comes through this screen of clouds, it gets bent or diffracted. And because the screen is blowing outwards with the solar wind, the diffracted waves sometimes come into the radio telescope and sometimes don't. And as shown in the bottom of the diagram, you get a rapidly fluctuating signal from a quasar. And you see the 1 second time bar, giving you an idea of the time scale. The other known objects in the radio sky were radio galaxies. They're relatively broad, extended things, and we viewed them both through clouds and through gaps in the clouds, all at the same time. And so the clouds blowing past didn't really affect the signal. So this is a very neat way to pick out very compact objects, such as quasars. Oh, that's interesting. Don't know what's happened there. Never mind. You look for a rapidly fluctuating signal, and it's a compact object or a quasar. But you do, my cursor is being a nuisance. I may have to get rid of it. We'll see. So you look for this rapidly fluctuating signal. At that time, the University of Cambridge had one computer. It was made with vacuum tubes. It had memory comparable with your laptop, and very few academics could have time on it. And Tony Hewish did not, so I did not. Our data came out on chart paper, and this is a sample of the chart paper, and it was my job to analyze it. The telescope produced 30 meters of this stuff every day. We scanned the sky in 4 days, so that's 120 meters per sky scan. And I observed for 6 months, so I had over 5 kilometers of this stuff. Huge amount of paper. I very quickly got used to identifying the quasars through their twinkling. Alas, radio telescopes also pick up interference. In those days, cars were badly suppressed, so a car driving along the local road could give you some interference. Anything that sparked, arc welders, for instance, anything that sparked inadvertently gave you radio signals. So there was quite a lot of interference, but I got used to identifying it quite quickly. Just occasionally in the 120 meters that was one sky scan, there was about 0.5 centimeter of signal that was a bit curious. And you see it here in this diagram labeled CP1919. It didn't look like a scintillating quasar, And it didn't look like interference either. There's some low-level interference here on the right. And they look different. If I unpack that just a little bit, the interference signal goes up and down, whereas this strange signal goes largely up. The interference signal is lower frequency. You can see chart paper between the spikes, whereas at least here at the left-hand edge, this is very high frequency. It does not look like interference. And I also knew, or very quickly ascertained, that if it was there, it was coming from the same bit of sky. Only in about 1 time out of 5 was it there. But if it was there, it was from the same bit of sky. This funny signal occupied about 10 parts in a million in the chart paper. But partly because of this imposter syndrome, doing my very best, so that when they threw me out, I wouldn't have a guilty conscience approach. I somehow remembered that there was this funny signal. And at one occasion, my brain said, "You've seen this signal before, haven't you? You've seen it from the same bit of sky, haven't you?" And then it's easy. These rolls of chart paper are in declination strips, and I file them in shoeboxes labeled with the declination strip. So you go get out the box for this declination strip, you lay out the charts on the floor. The graduate students were all in a large attic, and there was quite a bit of floor space. So you lay out the charts on the floor, you line them up by right ascension. You say, "No, it wasn't there. It wasn't there on that day. It wasn't there on that day. Yeah, I noticed that one that day. No, it wasn't. Oh, it might have been there. I didn't really notice that one. No, yeah, I noticed that one. No, yes, and yes, this one." And they all line up. They're all at the same right ascension and in the same declination strip. Then it gets easier. You go tell your supervisor and you say, "Tony, what do you think this is?" And he hasn't a clue. But he gives the grad student a job, of course. He says, "Look, this is all jammed into about 5 millimeters, 1/4 of an inch. We can't see what's going on. We need an enlargement." Fair enough. With chart paper technology, enlargements are easy. You run the paper faster underneath the pen and you get an enlargement. But you can't leave the chart running at that speed all the time because it gets through the roll of paper in 20 minutes. And guess who spends their time at the observatory putting a fresh roll of paper in every 20 minutes? Now, what happens is the graduate student has to go out shortly before the telescope sees this bit of sky, switches to high speed, and 5-10 minutes later switches back to normal. And I did that for a month, and the wretched thing had disappeared, and I made high-speed recordings of receiver noise. And my thesis advisor, Tony, was furious. "It's been and gone and done it, and you've missed it." It's always the grad student's fault. They're there for kicking. That's their main job. But I persevered and finally, after a month, got it. And this is the signal that came in. The labeling has been added later. You know that because of the 1. Nobody ever gives the first one the number 1. Only when you have more than 1 do you go back and number the first one number 1. So that label LGM1 is clearly later. The bottom trace is 1 second time pips, which were conveniently broadcast in those days, and we could put them on our charts. And the heavier trace above is the first pulsar signal. And you can see that there are pulses, some are missing, but when they're there, they're equally spaced at about 1 1/3 seconds. And even where they go missing, like under the letters LGM1, they come back again at the end, and they're in phase and with the same separation. Something is pulsing with variable amplitude with a period of about 1 1/3 seconds. I break protocols and I phone from the observatory to my thesis advisor. He's dealing with an undergraduate who possibly wasn't terribly bright because he wasn't in a very good mood. And I say, Tony, you know that funny signal? I've got it. It's a string of pulses, 1 1/3 seconds apart. Oh, that settles it. It's man-made interference. And he hung up. I knew it wasn't because I had been chasing this sufficiently long that I knew it kept sidereal time, and only astronomers keep sidereal time. It had to be something in the sky, but Tony took some persuading. I showed him all the records I had and how it was at constant sidereal time, so it was unlikely to be radio interference unless it was other astronomers. Was it faulty equipment? We enlisted one of Tony's colleagues and his grad student who had a separate radio telescope with separate receiver at the same frequency and asked if they could see it. And after a rather alarming false start, they managed to pick it up as well. So it's not that Jocelyn has wired up the radio telescope wrong, which my thesis advisor was considering as an explanation. But there's a big problem. These things give short pulses. This thing gives short pulses, which means it's small. But we already know it's keeping an accurate pulse period because I'm checking it every day. And we're able to measure this to 4, 5, 6 decimal places quite quickly. And it's keeping accurate pulse period, but it's small. To keep accurate pulse period, you'd think it'd be big. We now understand the explanation, but we weren't thinking too clearly then. It is small in size, but it's big in mass. We now know. A colleague managed to get a dispersion measurement. He took 2 of my receivers, tuned one up a shade in frequency and one down a shade, and saw that the pulse appeared first in the higher frequency, then in the lower frequency. This is the kind of dispersion you expect with radio waves, and the separation is determined by the number of electrons along the line of sight. Making a guess at the electron density in space, he estimated it was 200 light years away. So it's not something in the solar system, for instance. It's not a satellite in a funny orbit mimicking the sidereal day. Equally, although it's beyond the solar system, it's quite nearby in the Milky Way. So that was a little bit reassuring. It did look man-made. And as you see, it got the nickname LGM for Little Green Men. Tony argued that if it was being produced by little green men, they'd probably be on a planet that was orbiting their star. So we should look for the Doppler shifts in the period of the pulses as they orbited their sun. Jocelyn, will you please keep observing this, doing these fast recordings? So I did. We found a Doppler shift, but it was due to the motion of the Earth around the sun, because Doppler shift works for the observer as well as for the source. We saw no sign of a Doppler shift other than the Earth going around the sun. So we proved that the Earth went round the sun, but otherwise weren't making a lot of progress. And I stumbled on a meeting of Tony and the professor who was head of department and another person who edited one of the major astronomical journals. They were having a discussion about how on earth we publish this thing. We've still only got one. We're running out of tests to do on it. What do we do now? I stumbled on that meeting and left the end of it feeling rather miserable. You know, what the heck's going to happen now? Came in late that night to do some more of the chart analysis. the routine chart analysis for detecting quasars, because there was a huge backlog of this. It's about 5 to 10 at night. The laboratory is locked at 10. Grad students do not have keys. You can be locked in or locked out. And at 5 to 10, scanning the charts for another piece of sky, suddenly realized there's something that looks awfully like this first signal. Since I'm talking to astronomers, let me say, in Britain, Cassiopeia A, one of the strongest radio sources in the sky, is circumpolar. It does not set. 12 hours away from transit, it's transiting due north, and it's so strong I can see it through the back of the radio telescope. And this second signal was in amongst the mess of Cassiopeia A in its northern transit. I quickly get out some other charts for that declination strip, throw them on the floor, line them up. No, no, oh, it might be there. No, no, no. Oh, there's 3 sightings of it, all at the same right ascension. I need to be at the observatory to see that. It's about midnight, it transits. Right. Throw the charts on the desk, run out of the laboratory as the janitor is locking the doors behind me. Clunk, clunk, clunk. And at the appropriate time, go out to the observatory. It's December the 20th, pushing 21st. It's very cold. And there was a dry joint somewhere. And in very cold weather, the telescope didn't work. I cursed it, I flipped switches, I thumped the receivers. I got it to work for the right 5 minutes on the right setting, and in came pulse, pulse, pulse. The first one was at 1 1/3 seconds. This was 1 1/4 seconds. It's clearly from the same family, and now we have 2. This is real. I go away for Christmas with my boyfriend. We announce our engagement. It was kind of important we both got there, despite the pulsars. Come back, Tony's in a meeting, but he's kept the survey running and piled the charts unanalyzed on my desk. And I'm sitting there analyzing charts and suddenly realize that there's another one, what looks very like another one. I need to check it, but I'll just finish this piece of chart first and move on. And a meter further along, there's what looks like another one. 2 more on the same strip of chart paper. Tony turns up at that point, stands at the end of my desk. Look, Tony, look, look, look. Oh, Happy New Year, Tony. Thank you for keeping the survey running. Look at these, look at these. Huh. How many more have you missed? Go back through all your old records. I did go back through those miles of records, didn't find any more. We wrote up the first one for publication, and shortly before it appeared, Tony gave a colloquium announcing the discovery. There were 2 possible models for these things at this point: vibrating neutron stars, which had never been seen before, or oscillating white dwarf models. The white dwarf surface would vibrate, would launch shocks into the atmosphere of the white dwarf, which would give regular bursts somehow. Tony favors this oscillating white dwarf model. Everybody in Cambridge has come to this colloquium. Fred Hoyle sitting in the front row, and at the end of Tony's speech, he's the first to talk. He says, "This is the first I've heard of these things," in his good Yorkshire accent. "I don't think it's a white dwarf. I think it's a supernova remnant." And Fred Hoyle, from cold within 40 minutes, has hit on the right explanation. He was an amazing astrophysicist. The name pulsar was coined by the science correspondent of the Daily Telegraph. He asked us what we were going to call these things, and we said pulsating radio sources. He said, no, short name. What about pulsar? And pulsar they became. The image on the left is what we now picture them to be: a very small, compact neutron star rotating. swinging a beam of radio waves around the sky. And if the beam shines in your face, like now, you see a flash, and now, but the other beam doesn't shine in your face, so you don't see it. And that for a lot of pulsars, neither beam will shine in your face. We probably only pick up about 10% of them. The picture on the right is showing the pulsar's magnetic field and how the magnetic field is offset from the spin axis. And we believe the radio wave comes out the magnetic poles of the star, and it's a very, very strong magnetic field. So we now believe they're very small, very dense, neutron-rich stars called neutron stars. There's the mass like the mass of the sun jammed into a ball about 10 kilometers across. So the gravitational field is very strong. There's also very strong electric and magnetic, and they're rapidly spinning. They're probably formed when a massive star explodes at the end of its life, a supernova. They'd be the core of the star that gets shrunk, collapsed during the explosion. And they're observed primarily as radio emitting objects. But of the over 3,000 known, there's about 20 that can be seen in the visible, about 100 in X-rays, and about 200 in gamma rays. And about 10% of them are in binary star systems. One of them is a double pulsar binary. One is a triple system, and a few have planets. Now, how a pulsar has planets is an interesting issue. If it was a massive star with planets, those planets would likely be ejected when the star went supernova. Has it picked up the planets later? We don't know. And we suspect there's something like 10,000 of them in the galaxy. I'll go through this rather fast as I've been rather slow over the first part. So they have a mass a bit heavier than the sun, between about 1 1/4 and 2 times the mass of the sun. But their radius is only 10 kilometers. So their density is like the density of the nucleus of the atom. It's really very dense with some very bizarre physics. And we believe they're rich in the particles called neutrons, so they're also known as neutron stars. A thimbleful of this material would weigh the same as the population of the Earth, which I think is about almost 8 billion people now. So if you took those 8 billion people and jammed them into a thimble somehow, the thimble would weigh the same as if it was filled of stuff from one of these pulsars. And so these objects have got very strong surface gravity. There are also some tidal effects, and the nature of their interiors is unusual, to put it mildly, hard to understand. It's very condensed matter physics. The strong gravity, because of all this mass, bends light. If you stood on the surface of the star, you could see over the horizon by 20 or 30 degrees. Also, that strong gravity will redshift light. So if there were little green men on these stars, they'd look like little red men to us. And gravity also affects clocks. You probably know this from your sat-nav. The sat-nav did not correct for the effects of gravity. It would give you a position that was out by several kilometers. I will skip that one. There's a very, very strong magnetic field. 100 million Tesla, put that in context, your fridge magnet is probably 1/100th of a Tesla. So the electromagnetic forces are actually 100 billion times stronger than the gravitational ones. The physics of these things is amazing and really, really hard, because it's so amazing in so many ways all at once. Once you get a pulsar spinning, it keeps spinning, and they turn out to be very accurate clocks, good to about 1 part in 10,000 million. Or put differently, a typical pulsar's period has increased by about 1 second since the age of the dinosaurs. This means nature has provided us with some very accurate clocks dotted throughout the universe, and we're using them to test Einstein's theory of relativity. And Einstein's theory is testing very nicely. An initial question was this a rotating neutron star, like Fred Hoyle thought, or a vibrating white dwarf, like Tony, my thesis advisor, thought? If it's oscillating, vibrating, then with time, the period it vibrates faster. Whereas if it's rotating, as time increases, it rotates more slowly. When we found the pulsar in the center of the Crab Nebula, we were able to see that the period was increasing. So we know that these are rotating neutron stars. I've said a lot of this already. We know about 3,000 today in our galaxy or in the Magellanic Clouds. We think they're formed in supernovae explosions. They're rapidly spinning, radius 10 kilometers, mass like a typical star, huge magnetic field, huge electric field, and a really exotic interior structure. So pulsars can be used to test general relativity, as I've already said. They can be used to explore matter at high densities and high magnetic fields. We can use them to probe the interstellar medium, but come interstellar travel, we can use them as navigation beacons. And this has already been done on the plaque on Pioneer 10. This star-shaped thing in the left-hand half of the image is telling the aliens where we are with respect to a number of pulsars. The image along the bottom tells them where we are with respect to the solar system. The lines radiating out in that star shape, the length gives an idea of the distance to the pulsar, and the pulsar period is encoded on binary by little ticks on those lines. So aliens could find us. We can find our way around the galaxy because we fit a radio telescope to our spaceship and we say, there's that pulsar. And if we turn a bit, yep, there's this other one. And somewhere else, yep, there's the third one. And using the 3 pulsars, we can get a fix on our point where we are in the galaxy. So exotic as the pulsars are, they do actually have some uses, pretty rarefied uses, but some uses. So thank you for your interest. Thank you for your attention. And my apologies for going on a bit long. Thank you very much.
Dr. Bell Burnell, you could have gone on for 2 more hours. You should see some of the comments that we're getting here. One comment from Claude Plymate was how wonderful to get this front row seat to true astronomical history. I think that's the most fascinating presentation I've ever heard. And let me get the process started here if you'll take a few questions. How discrete are the beams from neutron stars, from pulsars? In other words, if a beam did not directly intersect the Earth, might a large enough receiver be able to detect one?
The beams seem to have quite sharp edges. So if it misses us, it misses us. But taking a leaf out of somebody else's book, maybe we could put a whole lot of satellites up in space with radio receivers on them to see if they can see some pulsars that we can't see. What do you think about a whole constellation of satellites, folks? Is that a good idea?
You'll find some people here that don't like some of the Starlinks. So anyone in the room right now, if you have any questions, or Scott, if you've received any from online?
Yes, there's, let's see. I'm posting back into our Zoom chat some of the comments, but which are numerous. Jerry Cheney, who's watching on YouTube, wants to know, do all neutron stars begin life as pulsars?
Have we terminated the screen share?
I terminated briefly. I can put it back on, but I think that blinking screen is Can I put it back on? Ah,
Yeah,
interesting.
I can stop it. Here we go.
Okay, there we go.
Okay, thank
There we
you.
go.
I thought the blinking was maybe going to give somebody an epileptic fit.
I'm sorry, Scott. What was the question again?
So the question from Jerry Cheney from YouTube is, do all neutron stars begin life as pulsars?
Probably not. We also know of neutron stars that are in binary systems with another massive star, and they are X-ray emitters. They do pulse a bit, but not necessarily and not in the same way. So I think there's neutron stars, and some are pulsars and some are not. And of course, some may be dead pulsars, which is the other thing, because these things will ultimately slow down and not have enough oomph to produce a radio beam.
Thank you. A question I had, if pulsars are created in supernova, are they ejected out of a supernova explosion, or is it kind of what's left after a supernova explosion?
Certainly in the case of the crab, it's what left. You find the crab pulsar well within the nebula, where it belongs suspected was the site of the explosion that created the nebula. But we do also know of some pulsars that get ejected because we can see them moving across the sky.
Mm.
So sometimes they stay put and sometimes they get given quite a big kick and have velocities of hundreds of kilometers per second.
Very interesting.
What is the slowest period you've run across with pulsars?
It's probably about 6 seconds. There seems to be some dying off as you get to the longer periods. Presumably, if they rotate more slowly, they don't have enough oomph to produce a beam of radio waves.
I'll just read one more comment here. Dawn Monroe Davies, who's watching on Facebook, she says, what a phenomenal presentation. Thank you, Dr. Burnell, for your amazing contribution to science and for sharing your work with us today. Thank you, Astronomical League, for giving us the gift of Dr. Burnell as this year's keynote.
Thank you very much for those kind comments. And it's a real pleasure to be with you.
Any other questions from anyone?
David Macaulay is asking about the radio arrays and how they were steered to a particular array and deck.
It's the magnetic field of the pulsar. These radio beams probably come out at the magnetic poles where the field lines are open. They don't curl around and join up, join back up into the surface. And it's probably the open field lines that produce, it's in the area of the open field lines that the beam comes out.
Okay.
Well, Dr. Bell Burnell, again, I can't thank you enough for joining us. We will be sending you a little remembrance of this keynote address, and I want you to please convey to your assistant, Tanya, our appreciation. She was just wonderful to deal with. She was very friendly and helpful at all times. And
Yes,
thank you so much for joining us. It was a great honor to hear this and to meet you.
Thank you very much for listening. It's my pleasure.
Okay,
Thank you for the opportunity to be with you.
Okay, good night.
Hope the rest of the meeting goes well.
Thank
Bye-bye.
you. Bye.
Thank you.
Wow.
Yeah. Wow.
Yeah, some other
That
questions
was
that are coming in
amazing.
actually now, but someone wanted to know, how was your eye trained to read graph details? Was it music training? So, don't know. Don't know.
That was amazing, though.
That was amazing. This was like,
Yes.
such a rare experience to, get a firsthand account like that. Also very personalized about her struggle with imposter syndrome and, just and what it was like to make the discovery, the struggle of it and everything. So it sounded like she really had a tough time during those days.
Definitely did.
Well, there were lots of situations that she faced, where they were interviewing Dr. Hewish and her. They were asking him technical questions about pulsars and asking her about,
Trivial things.
trivial things, that were frankly quite sexist. And it was a hard time for women to get into astronomy back then. And fortunately, we're seeing those barriers knocked down, and just so many fantastic professional astronomers now are women, and they're contributing enormously to the science. So,
But she brings it home to how women really had to struggle way back then. I find it amazing to hear her speak about what she went through, the feelings that she had, the pressures. I know there's always going to be pressures, but for back then, she had left her homeland. She went to a completely alien place. I think that took amazing courage and amazing drive to want to do what she did. And that's the kind of inspiration I think people everywhere can respond to.
you can read a similar story if you read about Lisa Meitner and working with Otto Hahn on splitting the uranium atom the first time in Germany. There's actually a great YouTube about this. And she had a terrifically difficult time getting any recognition at all for her work in splitting the atom. I mean, it was just an incredibly unfair situation. And if you read Dr. Bell Burnell's background, you'll find the same difficulties back then.
Yeah.
And
there was a question, I didn't ask it directly, but how long was it before she was actually recognized and respected for this discovery?
I think she was recognized pretty early, but the recognitions have just been flooding in. If you read her Facebook page, there are so many awards there. This breakthrough prize, $3 million, which had no time limit on the research. It was for her pulsar discovery. And so I don't know. I think if you looked at her Wikipedia page, I didn't mean Facebook. If you look at her Wikipedia page, you will see the dates of the awards, and probably they're mostly in the 90s and after. But
she was getting awards. She got the Michelson Medal in 1973, jointly with Dr. Hewish.
Yeah. My good friend Richard Gott, who's here, by the way, and who spoke the other day, commented very wisely, who won? If you ask people who discovered pulsars, they'll give you Jocelyn Bell Burnell's name. They don't know the person who won the Nobel Prize for it. So
I can identify with this so much because I think we're about the same age. Because I went to KU, and they keep telling me that I was in the wrong classroom in the trigonometry and my physics classes. They say, well, you couldn't possibly want to be in this room, because they really didn't think that a woman would even take it. So
I have a question I would like to pose. I believe that this experience is one of the most valuable experiences I have ever had with the Astronomical League. And my question is, could you describe the process by which you genii were able to get Dr. Bell Burnell to enlighten us today?
I wrote her an email. That's all. Go big or go home. You might as well try. Nothing is gained unless something is ventured, David. And I wrote a nice email to her and received a wonderful response. So we're very grateful for her help with this.
Yeah.
Well, Chuck, I must congratulate you. And this certainly was exciting. More than exciting, it was earth-shattering, space-shattering for me and Wendy today.
Thank you.
And these conversations that we're having now is, if you're looking at a group like the Astronomical League, is definitely about diversity and inclusiveness. And, so it's, it's awesome to see it played out here on the Astronomical League convention.
And Terry and Don have done such work. Terry and I have been working together. She's kept me sane, and I hope I've kept her sane just from our humor through the development of the convention. And we talked about whether to, who to invite as speakers, and we've collaborated on that. And I just happened to be the one that wrote the email, and it was Dr. Burnell who agreed to appear. So I think all credit goes to her and her assistant, Tanya Gujral, who was very, very friendly in her interactions with us and Dr. Bell Burnell in planning this. Okay, we go move on now. And Terry, I believe you have a presentation to make.
Yes, I do. I would like to introduce the 2020 Horkheimer O'Meara Journalism Award winner. Her name is Lucia Castillo. And each year, the Astronomical League conducts a major science writing competition for youth ages 8 to 14. The winner of the Horkheimer O'Meara Journalism Award receives, do what?
Yeah.
Okay, I thought I heard somebody talking to me. Okay, receives a beautiful plaque and a $1,000 cash prize funded by the Horkheimer Charitable Fund. Lucia Castillo will be in the 10th grade this fall at Willows Academy in her hometown in Des Plaines, Illinois. Her and her family members of the Northwest, her and her family are members of the Northwest Suburban Astronomers. As the first place winner of the Horkheimer O'Meara Journalism Award in 2020, when she was finishing 8th grade, she received a check for $1,000 and a first place plaque recognizing her splendid achievement. Compliments from the Horkheimer Foundation. Her well-written essay is entitled, How Kids Can Be Interested in Astronomy. So if you are here, Lucia, would you like to read your entry?
I think she's probably a rising 11th grader now.
Yeah, that's probably true.
I actually am a rising 10th grader.
Oh, all right, okay.
Yeah, but I would like to read my essay, if that's okay.
Great, go right ahead.
Okay. How kids can be interested in astronomy. Astronomy is a very important factor in our lives, and it interests many people, but in my opinion, it interests mostly adults. Astronomy should be a topic that appeals to all ages. Because astronomy is the study of objects outside the Earth's atmosphere, it can satisfy our fundamental curiosity about the world we live in and answer the big questions. Some ways that kids could be more interested in this branch of study is to make learning fun, simple, and interactive. A way to get learners interested in anything is to make the lesson fun. Especially for kids, when you do something fun, they will remember it more. For example, on August 21st, 2017, there was a total solar eclipse where the moon blocked 100% of the sun. I remember my mom took me and my 6 younger siblings to the Alder Planetarium in Chicago. We stood out on the porch and looked at the eclipse with special glasses to protect our eyes. We stood out, it was so cool how you could see the moon slowly cover the sun as the sky became darker. Afterwards, we went inside to watch a movie about the eclipse looking up at a huge screen. This event was very fun and it made me more interested in learning about astronomy. Another way to get kids interested in astronomy is to make it simpler for them. One way to do this is to have them use binoculars instead of telescopes. Even though a telescope may seem fancier and more advanced, some star clusters are better seen with binoculars. For example, the Pleiades is better seen with a pair of binoculars because telescopes may theoretically show fainter stars, but they can only show small parts of a cluster. Binoculars are also easier to travel with, lighter to carry, and much simpler for kids to use. Another way that will get kids excited to learn about astronomy is to make it interactive. I do lots of experiments in science. Experiments are a type of hands-on activity that make learning interesting. Observing the sky with your eyes, binoculars, or a telescope is a hands-on activity where where one uncovers the beauty and magnificence of the celestial world. Twice every year, I go up to Wisconsin to visit my grandparents. I have great memories of going out at night and looking up at the stars through a telescope with my grandpa. In Chicago, I can't really see many stars because the city lights are so bright. When kids are able to go out and observe, they have fun and become more interested in what they are learning. I've only mentioned 3 of the many ways to get kids interested in astronomy. If the activity is fun, simple, and interactive, there will be no trouble in captivating kids' interest in astronomy.
That was amazing. Thank you. I'm curious, have you learned the constellations? What is the first thing about astronomy that really drew you to astronomy?
Well, I have memories from since I was very little of, like I said in my essay, I was going in my grandparents' house. They live in La Crosse, Wisconsin. And my grandpa would always have this telescope and he'd point out certain constellations. And I remember always trying to figure out where the Big Dipper and the Little Dipper were. Those were my favorites.
Yeah, definitely. And I think watching the wintertime come around with Orion coming up too, such bright constellations. Well, that was an amazing article or amazing writing there. And I think that's great information and really good things for all kids to look at, and even some adults, because I think sometimes when the youth writes about what they are actually seeing, it brings back times in your life. Just as you're talking about your grandpa and seeing your grandparents, I actually went to my grandma's, and that's where I could see the stars the best. And I would lay on the hood of her car and look at the stars. And I was about your age when all of that started. So it's amazing to me how many times we see stories intertwined. So thank you so much and congratulations. You have done an amazing job. Your plaque looks beautiful back there. Keep up the good work.
Thank you.
You're welcome. All right, Chuck, I think we have door prizes.
Door prize time. Okay.
Door prize time.
Okay, I think the first one up is an Astronomical League door prize, an Explore
All right.
Scientific gift card for $250. And I will go ahead and go to the random number generator. What is my total number again?
Yeah, hang on. I knew you were going to.
Sorry, I keep asking. It keeps changing.
827.
827. Okay.
Yes.
And the number is 208.
Got it.
Okay.
Okay.
We're good on time, so we'll just wait until you find it.
Okay.
The way we do this, Terry has a list and an Excel list that's numbered with all the registrants, and only she has it.
And naturally, it's right where it's stapled on the name.
Okay.
It never fails. It's always something like that. It is Stephen Chapman.
Stephen Chapman. Stephen, congratulations. Got a nice gift card coming to you. Okay. Stop sharing here. I'll tell you what, I'm going to, before I call on Mr. Scott, I'm going to draw another number so Terry can be looking it up.
Yeah.
And that will be number 53, Terry.
Thank you.
And now I will stop sharing and ask if Robert Scott is here. Hello, how are you?
Hi, good afternoon.
Would you tell us a little about the prize you're offering?
Okay, let me see if I can figure out how to share my screen here.
Okay, should be a green button on the bottom.
Okay, can you guys see it?
So far, there you go. Perfect.
Okay, besides being a coordinator for a couple of observing programs, I make tables for prizes for star parties that I go to. And when you guys put out the call for door prizes for this, I figured maybe you need a table to give away. So I got in touch with Mark Simonson because he does awesome wood burning. And I said, if I make 2 tables, would you would burn the Astronomical League logo into them? And he agreed. So he gave a table away yesterday, And here's a picture of the table folded. And there's a picture of his wood burning of the logo.
That's
And
great
so
work.
we're going to give that table away, but I want to first talk about, since I'm a coordinator for 2 observing programs, I'd like to mention those. The Bright Nebula program, which you just revised the list to 250 nebula you can pick from. And it can be either done imaging or it can be done visually. It's a challenge visually. So that's one of the 2 programs I coordinate. And the second program is 2 in a View. And that's a program I actually originated. And it has 109 objects, which you have to do 100 of. So you get to pick what ones you like. And it's a little unique in that fact that you can actually make up 15 of your own 2 in a Views and get credit for those as part of your 100. And we've had one person actually make 14 in their submission. So those are a couple of observing programs that you could try out. And a lot of people, their main interface with Astronomical League is through the observing programs. So I think it's quite important we have these. Anyway, let's give a table away.
Okay. If you could close the screen share for us. And I would like to say that I did the 2 in the View program, and I'm almost done with the Bright Nebula, and really appreciate your work as a coordinator. I know it's tough. I coordinate 3 of them myself. It keeps you busy. And a great job developing the 2 in the View program as well. Terry, who won the table?
Robert Borowski will be receiving that table.
Okay. What was the number again on that?
The number was 53.
53, thank you. Okay, we're now looking for Ernie Jacobs. Are you with us?
Yes, sir.
Okay, I'm going to go ahead and draw the number first. And I believe the prize that you will be giving away is an Explore Scientific gift card for $250. Is that correct, sir?
I believe it's with ADM accessory.
ADM accessories. Okay, I'm sorry.
Correct. Yeah, Anthony is actually a member of our group. He's located here in Western New York. So we're very pleased to.
I had down that it was a local
yeah.
group, and I wrote that down wrong. Okay,
Yeah.
And let me draw the number. That will be number 8.
All right, thank you.
Should be easy to find. Hopefully.
Yes, it is.
Okay, Ernie, why don't you tell us a little about the Buffalo Astronomical Association?
Okay. Is it all right if I share my screen?
Absolutely.
All right.
We're good on time.
Okay, because I have 3 slides and I have a 2-minute video.
We have plenty of time for that. Go ahead.
Okay. So
have you when you click on, is the video audio?
yes, it does. Yes,
Okay.
it does.
Did you click on share sound when you started the share?
Before sharing the video, I'll unshare and reshare. I did not click on share sound.
Okay.
Apologize. So real quick, our club started back in the 1930s with 2 clubs that were associated with the Buffalo Museum of Science, one concentrating on telescope making and the other on observing. I believe in 1952, we became one club, the Buffalo Astronomical Association. And to this day, we partner very closely with many educational science institutions and schools in our community. Currently, we have about 130 members with monthly meetings September through June, monthly public observing at our observatory at our dark sky site, which is located on the grounds of the Buffalo Audubon Society property in our area. It's about 45 minutes east of Buffalo to get away from the lights. And we do numerous public observing at local parks, libraries, schools, etc. And just regale you with a couple of pictures from some of our events at our observatory and local events. So I'm going to stop my share real quick. And I'm going to share with sound. And this is a video that our vice president put together. It's 2 minutes and 17 seconds. That's just a little tour of our observatory.
Welcome to the Beaver Meadow Observatory. The Buffalo Astronomical Association maintains a dark sky observatory on the grounds of the Buffalo Audubon Society's Beaver Meadow Nature Center in North Java, New York. The facility houses the club's varied instruments, which include this 20-inch obsession telescope, one of the largest telescopes for public observing in Western New York. The BAA is a not-for-profit community organization that provides astronomical outreach, STEM education, and public programs. Our efforts and ability to provide these, along with any observatory or equipment maintenance and upkeep, is solely supported by contributions, so any donations are greatly appreciated. We also maintain telescopes that can be borrowed by members, including the Celestron Nexstar 6SE, donated in memory of Sherry Harper and her outreach efforts, a Meade LX200, and a Meade refractor. Now you may have wondered, where is your observatory and telescope kept, as you have not seen a dome? Well, up here is where we have a 14-inch Celestron Schmidt-Cassegrain telescope and a Teleview NP101 refractor mounted to an Astrophysics 1200 mount that can be controlled from the computers in the other room. These telescopes can be used for viewing as well as astrophotography. Of course, you have seen that this building has a roof. This roof actually rolls back. What? You don't believe it? Well, I guess we'll have to show you. Thanks for joining us, and keep looking up.
Okay. The Cub Scouts and Girl Scouts and generally kids that come to our observatory love to open the roof.
Yeah, well, that astrophysics mount's sweet too. That's a beautiful facility.
I love that sound.
One of the incredible things is we've had over 40 societies that have shared their clubs and their club activities and outreach with us. And then you just extrapolate that over 310 league member societies that are all doing this. You can imagine the extent of the outreach that gets accomplished. Thank you so much for offering such a nice prize. I know you rely on donations, and now you've donated. We really appreciate it. Thank you.
Well, thank you. That presentation by Dr. Bell Burnell was just, I'm still shaking. So thank you.
Thank you. Okay. Is Mr. Garfinkel with us?
Oh, wait a minute. Wait, we haven't announced the winner yet.
Oh, I'm sorry.
That's okay. Rich Kraling will be going shopping.
Would you repeat the name?
Rich Kraling.
Kraling. Okay. Congratulations, Rich. And let's see, Robert, before we go to you, I'm going to draw the next number so we can let Terry get started on that. That'll be number 203, Terry. Okay.
Thank you. Got it.
All right. I didn't show that, but I hope people will trust me. Okay. Okay. Mr. Garfinkel, are you with us?
Hello. Glad to be able to give a private donation. I do belong to several associations, but I'm not sure if the East Bay Astronomical Association and San Jose Astronomical Association are still members of the league. They used to be when I joined 30 years ago. Anyway, since all these other clubs keep saying when they were founded, I started in July 1947, just 5 months before the founding of ALPO. I received my Boy Scout Merit Badge in Astronomy in 1963. I was elected a Fellow of the Royal Astronomical Society in 98. And Asteroid 31862 Garfinkel named for me in 2018. As a kid, I always wondered what, or on the moon, what features were named for, who or what, or whatever. And so I started writing Luna Cognita as a nomenclature-only book in 1989, while waiting for the publication of Star Hopping Your Visa to Viewing the Universe, which I do happen to have a copy right here. It's still available on Amazon as a print on demand. It has sold over 15,000 copies worldwide. Okay, Luna Cognita, I used the Latin words, which means the known moon, because Latin was the language of science for centuries. The book is full of history of the moon, the people who were involved, like all the people in photography who have names on the moon and such like that. Even though film is no longer used very rarely anymore, these people were still involved in all of that and have their names honored. I use the Latin title also because there's so many books that say the moon followed by a subtitle, whether fiction, nonfiction, poetry, and such. So I figured my book would get lost. Luna Cognita consists of 3 volumes, approximately 1,800 pages, 1,120,000 words, and 1,365 figures. I do talk about lots of history of the people. Okay, it's in 32 chapters plus 15 appendices. Harrison Schmidt, who I understand is going to be the main speaker at the next year's convention, he wrote the introduction for the book. I met Harrison on a total solar eclipse trip in '91, and as Ed Krupp called it, the mother of all eclipses on that ship. And he accepted my asking him if he'd write the introduction to the nomenclature book. Well, the book kept growing and growing and growing as I added more stuff to it. The glossary is now just 78 pages. The bibliography is 86 pages, so you can see how extensive the research that I did on it. The retail sales price is $89.99, and the one price is for all 3 volumes. Now, I mention that because Amazon keeps screwing up and sending out a single volume to a single customer. So one customer gets volume 1, one customer gets volume 2, and one customer gets volume 3, even though it says right here on the cover, volume 1, volume 2, or volume 3. And they come wrapped together in cellophane with a big banner, do not break. Amazon keeps sending them out. They've done that to other Springer books. Now, Springer printed the book, published the book, and so you can either get it from Amazon and you might have to pay shipping. Springer does not charge for shipping, and they know how to send out all 3 books, okay? So the other thing is, when I was writing book reviews and I wanted to review another book by a friend, and I called Springer, and the gal said, well, what are you doing? I said, well, I'm writing a big book on the moon. And she got so excited, I thought she was going to wet her pants or something. She says, we're looking for a big moon book. At that time, Luna Cognita was only 1,100 pages. And so I said, well, how big, and they said, just keep writing till you've got everything in it that you want to have in it. So that was in 2011. It just kept growing and growing and growing. I finally said, after 30 years, it's time to get it published. So that's my donation. I appreciate the opportunity to donate it to the club. And I have been watching many of your friends, my friends, like Don Mockholt, who wrote or helped me with the Messier Marathon in star hopping. We were both in the San Jose Club at that time. And it's the first book in which the Messier Marathon was printed. Then he did his own book. And Scott has been a good friend of mine over the years. We met many, many years ago. Anyway, again, thank you very much. And I hope the winner enjoys it. The book will be coming directly from Springer. They will ship it directly to that person.
Fantastic. Thank you so much, Robert. I appreciate it. Congratulations on putting together a fantastic set of books. That's amazing.
Yep.
Terry, who's the winner?
Yep. Scott Jacobson.
Okay, Scott, you got some nice prize coming. Okay.
Scott.
Okay, that'll take care of it for session 9. When we come back, we have 2 excellent talks. One, as it happens, on Back to the Future Lunar Exploration, by Dr. Caitlin Ahrens, and we have Dr. Larry Crumpler, who will be with the Perseverance team. So 2 really interesting talks coming up. Come back and join us at 4:45 Eastern Time. That's about 13 minutes from now.
Okay, so we'll go on the break.
Okay.
Robert, it was nice to see you again. This is Scott.
Just a word, remember everyone, we're still live during the break. Carol?
Yes,
Hi. You have closing remarks tonight.
correct.
Yeah, okay. Just want to make sure.
Hello, everybody. We're back. We've had some fantastic lectures and some amazing door prizes already given out. If you haven't already done so, and if you think that what you're seeing here from the Astronomical League is beneficial to you, and you haven't already become a member, you should probably do so now. I'll be placing a link in chat, and you can check it out, but there are many benefits to being an Astronomical League member. Not the least to mention, there are I think over 80 observing awards, observing programs that they have. So lots of good stuff from the Astronomical League, the world's largest federation of astronomy clubs. I'll turn this back over to you, Chuck.
I will just display one slide and then give it to Terry. And this is just to remind our audience. Whoops. Can you see that?
Yes.
Yeah. I'll just let that post for a few moments.
And there was a question, Chuck, about the discount that was on Springer. And if Robert, if you could put the link in chat, I'll share that with the audience.
Robert's book has sold over 2,000 copies in hardback and over 100 ebooks since it was published as well. So if you'll publish that link, that'll be great. Terry, take over.
All right. All right. Well, Chuck has pretty much told us what's coming up this afternoon. We have Dr. Caitlin Ahrens coming up. We have a sketching award and Dr. Larry Crumpler coming up from the Perseverance team. So let's start. It is with great pleasure that I am going to introduce Dr. Caitlin Ahrens. Caitlin is a graduate of West Virginia University with BS degrees in geology and physics, astrophysics. Her research background includes theoretical seismology, mineral analysis on the Martian surface, and radio astronomy. In the spring of 2020, she received her PhD in space and planetary science at the University of Arkansas on her research simulating Pluto's conditions in her lab to create various ice phases and researching Plutonian glaciers. Currently, Caitlin is a NASA postdoctoral program fellow at NASA Goddard Space Flight Center, working on lunar ices and lunar impact craters. In 2018, Caitlin was awarded as one of the 10 outstanding young Americans. And I want to add to this, Caitlin is also a past Horkheimer-Dioria Award winner, which is just amazing. She is one of those people that I have had the pleasure of knowing for a while and knowing her mother. And she is one of these people also, just as we've done with ALCon this year. You sit back and say, I cannot wait to see what this girl does. And she has been going ever since. So Dr. Ahrens, would you want to take it away?
Thank you so much, Terry, for the amazing introduction. I have to give major round of applause and props to the Astronomical League for accommodating hectic schedules. My brain is still very much fried from this past week working on some intense Venus concepts going on between different kinds of planetary science communities and with JPL. So thank you so much for accommodating my hectic schedule, and then that I could actually have an awesome keynote for you guys today on lunar processes. So switching my brain between Venus to the moon today. it's gonna be interesting. So let's hope that I can stick with at least the same planetary body today, shall we? Although I'm happy to answer any and all planetary questions that everyone may have. All right, so can you see my screen? Awesome. All right, so I'm seeing thumbs up. All right, so Back to the Future lunar exploration. We're all major fans of the Apollo missions, and then prior to that, with just the whole exploration of the moon. And the moon itself is an interesting natural satellite of Earth, and it has so many different kinds of mysteries. Now, when I started out in planetary science, I was originally with Mars, and then I moved out to Pluto with New Horizons. And so when I was applying for this job with the moon, my planetary geologist side was like, wait a moment, what is still interesting about the moon? I think I guess the lunar community though, but as a geologist, it's like, what's new? It seemed to me that there was already enough going on. Luckily, I was very wrong in that regard. So just looking at this picture in itself, you're like, okay, there's pretty craters, there's mare, which originally we thought were just beautiful oceans on the moon. Now they're actually just very soft, very less cratered lunar flows going on here. It's just beautiful. But within the craters and all the different kinds of compositions of the lunar rock, what's happening at the North Pole versus the South Pole of the moon, there are still plenty of mysteries. So taking a look a little bit into like the geologist side in me, just looking at the different kinds of lava flows, how did they kind of bleed out into these craters and basins to form the mare? What kind of crater processes can we actually see on the moon? Some of these riles and rifts that have actually split open and cracked open the surface of the moon, and maybe some lava tunnels, that some like lava tubes that we would see here on Earth. Could we explore lava tubes on the moon and eventually to Mars as well? And then also you just have this fantastic geophysics going on. The moon is still very much dynamic in just its own way. We think dynamic with the Earth as being volcanic and earthquakes and tornadoes and so on and so forth. But with the moon, it definitely has its own definition of what is considered dynamic. And so seeing all these pieces of like cracking and making cliffs, very large cliffs, like the one, this is a very large cliff and then graben system I'm currently working on with some colleagues now, actually. So in brevity here, we've explored so many different locations on the moon, and we've just barely scratched the surface of lunar exploration. So it's fantastic to see of all of these different kinds of landing areas, but there's still so much that we need to do. So let's get started by looking backwards in how we are moving forwards. We're going to start with the lovely 1959, Luna 3, Pioneer 4, Luna 1, and then onward to Rangers. So these were definitely our first flybys of the mission, just to make sure that we even have the technology to even just now, when I mean flyby, I don't mean it just stayed in orbit. When I mean flyby, it truly just was like a very quick zip. Hey, look, we went past the moon, hooray. Okay, good job, pat on the back. Okay, we're done. So barely taking pictures at this point, but it was truly just a technological feat of, can we even just get past the moon, and can it radio signals back and go, hi, I made it, there was the moon, and goodbye. But I do want to have a quick mention about Ranger 4. This is a fantastic news article that I found about Ranger 4 crashing onto the moon. And going through the article, there was one piece of this article that I had a very fun time with. It had nearly 6,000 mph crash onto the lunar surface, though. But I gotta love the bottom part here, where it was heartwarming that after 6 failures, it had a bullseye. Yeah, we totally meant to hit the moon. But 6,000 miles per hour, that was very, very impressive, to say the least. But in that case, with all the technology, we're like, okay, we now know how to get to the moon, but let's really get started. Let's really figure out what kind of instruments and experiments that we can really have with landers and eventually rovers and even orbiters as well. So getting to work. So the 60s and then into the early 70s was just this huge boom of orbiters and landers, and then eventually to human exploration of the moon. So I do not have the time to go through every single one of these. And I'll provide links at the end of my talk, though, on how you can explore every single one of these missions. They are beautifully archived by the Lunar and Planetary Institute. But I will mention a few fun facts about some of these missions, though. So Zond 3, if you were to look up Zond 3 lunar images, they're actually really beautiful. I really appreciate Zond 3 imagery in this case. It almost has a neat black and white sci-fi film feel to it. You can almost hear the theremins woo in the background, kind of deal. So beautiful images from Zond 3. Surveyor 5. Some of the Surveyor images previously with 3 and 4, kind of gave us some very rough images, though, but I really appreciate Surveyor 5 in this case because it really gave us a sense of the texture, how rocky the lunar surface was. Now, looking at this image, you wouldn't think we still didn't have a grasp as to, is it rocky hard or is it rocky soft? In which case, it's almost like, is it flour or is it just cement? What's our scale of hardness here? So it took us a while to figure that out. But the beautiful boom of Apollo missions really gave us the strength to figure out experiments, more so with human exploration and just seeing if we can carry all this technology to the moon, around the moon, and then back to Earth. And then our sample returns from the Apollo missions as well. So again, I'm not going to go through every single Apollo mission because that's a lot of coverage to go through. But I will say that it's interesting to see where all the landing sites were. And then some of them have also been very close to some of the Luna and Surveyor sites as well. So we typically stay around the middle equatorial region of the moon. We will be exploring the polar regions at the moon soon, and I'll get to those here in a bit. But some of the panoramics that we get from the Apollo missions are just absolutely breathtaking, and I highly encourage everyone to just go find those panoramic pictures. They're just absolutely awe-inspiring. Just to see the cool mountains and really makes you feel small within the craters. And then when you see lunar maps, you realize how small those craters actually are. We didn't really get to explore really, really, really big craters, but and just enough to go like, oh, that's some pretty good hills there. Another panoramic. So looking at all the really interesting textures between how smooth some of the landscape looks and then versus some of the really rocky textures, differences between the Apollo landing sites. It's really fascinating. I gotta really mention astronaut Harrison Schmitt as well. I have also talked with him about the orange soil, and he loves telling this story though. So think of this, December 1972, they get this slightly discolored soil going on here. So it is slightly orangish. They kept taking pictures of this area, and even on the moon, it's like, there's this orange soil. Why is it orange? We know the moon to be, several different shades of gray at this point. And there's this one rough spot of orange. What in the world is going on? And so they were so excited. We found orange soil for some reason in Shorty Crater. Let's bring it back to Earth. And Harrison was like, oh, this is great. Like, what in the world is this stuff? They get it into the lab and they open it up, and it's just black and brown. It's like, why? What happened? Did they open it wrong? Did it get oxidized? Like, what in the world happened? And turns out it was just a matter of how the glass inside the soil was actually reflecting the sunlight just enough to make it appear orange. So in reality, it was just the volcanic glass. This volcanic glass, turns out it was from a volcanic eruption that happened 3.64 billion years ago. So very, very fascinating stuff. And not always everything of what it appears to be, though. But glad that they took a bunch of pictures for us to see, like, yeah, okay, don't worry, Harrison, you weren't going crazy. There is some discoloration there. But not orange. Orange on the moon, but not when I got back. So there's this fantastic atlas, the Lunar Sample Atlas, part of the Lunar and Planetary Institute. Again, I'll provide the link at the end of my talk. But this entire atlas, you can scroll through and just click for hours and hours and hours of different rock samples that have been acquired, and the different names and what missions, the astronaut notes that are with some of these rock samples, and then even what some of the thin sections look like. So how thin sections work is that you have a moon rock, and then you would have to splice it very, very thin, and I'm meaning like less than deli salami ham thin of the rock samples. And what these rock samples that do is that you put them in between two plates of glass, and you put it under a specific type of microscope. I like to call it a tunable microscope, but it could also be called the mineralogist microscope. But it's typically a microscope that has a turning table. And this turning table has two specific bulbs or light sources at the bottom as well, and it's called cross-polarized light. And what happens here is that certain minerals actually give off different kinds of colorations. So if anybody picks up an introductory mineralogy textbook, this takes up a good couple of chapters of colorations and birefringence, and at this point is really pretty colors and really pretty lunar rocks. But what I wanted to mention here, though, is that every color that you see here is just a different kind of mineral, and there's so much that we can still learn with these thin sections. Not only the different pretty colors and what minerals are involved, but then how are they shaped? And you can see how differently these two have been cracked and almost shocked in this lunar rock. And these two thin sections are in the same lunar rock, which I think is very interesting. So 1973 all the way to 1994, it was a bit of a quiet period with lunar exploration, because the Apollo programs gave us so much to work with, all the pictures and the samples that we're still working through the samples to this day. And so it kind of gave us a bit of a lull at this point. We were pretty much focusing on Mars. At this point, we were focusing outer planets with the Voyager programs. we were trying to figure out with Venus as well. So we were pretty much like, okay, we need to kind of, put a little brake pad on the moon, and let's go have fun elsewhere. I do want to have a soft spot for the Hitten mission here. This is from the very early stages of the Japanese Space Agency. Launched in 1990. It was only a 3-year mission. Very, very small, compact, not much fancy instruments with Hitten. Hitten, however, is Buddhist for flying angelic creatures, by the way. So Hitten had a very interesting history, but it is the first aerobraking mission at this point. Usually you have either orbiters that try to stick to around the lunar orbit, or it was truly just flyby. But Hitten really encompassed the using of the moon to use as an aero brake point. So that worked out really well. And a little note on Clementine. So Clementine now gave us mineralogy maps, or at least the start of it. So very low resolution at this point, but the mineralogy of the moon still fascinates us and still eludes us rock nerds, So looking at all of this bright pink, don't worry, the moon is not this bright pink and blue. This just happened to be the color scale that I chose for the day because it looks really pretty. But all this bright pink that you see here is all the really cool iron that we would see on the moon. So Clementine there for a while, somewhat satiated our need, our thirst for knowing what kind of minerals are going on here. But in the sense, Clementine only gave us what was titanium rich and what was iron rich, and that was about it. So 1997 all the way to 2011, we're starting to come up with new technologies, and let's strap those new technologies onto orbiters now. So now we're really concentrating on more orbiter, not so much surface instrumentation, higher resolution images. What can we improve about the mineral maps? Where is all the cool water? Which is now the fancy buzzword for lunar sciences, though. But I do want to go into a little bit of the Lunar Prospector. So Lunar Prospector was only a 19-month mission. It went into low polar orbit. And then in 1998, as you can see with the lovely purple trajectory there, and then we specifically wanted it to crash into the moon. So this was ALCross. Acronym escapes me at this moment though, but we intentionally crashed it into the moon. And what happened then was all the orbiters and even some radio telescopes on the Earth immediately were like, okay, we're waiting for the impact. We're waiting for the impact. We waited for the impact. There's the impact. Okay, to all the instruments turn on, and let's just sniff the heck out of this plume and see what turned up. So we did confirm water ice with a Lunar Prospector. So hooray. So the Kaguya mission now gave us our better titanium versus iron mineralogy maps several years after Clementine. So now we can see kind of a different resolution style between Clementine on the left here and then Kaguya on the right. So still some interesting resolutions going on here though, but they essentially almost match up, but the resolutions of Kaguya are much higher. Oops. So this is my main job now is with the Lunar Reconnaissance Orbiter. Lunar Reconnaissance Orbiter began in 2009, is still going strong. A myriad of instruments on the LRO. LRO also produces some beautiful calendars every year as well. So, so if you need a calendar or just really want some really fancy lunar pictures, they come out with a calendar every November, I believe, is when they start taking in orders. So Google for that. It's really beautiful pictures, and I have one in my home office across the way here. But LRO has, like I said, has a myriad of instruments. In this case, it's no longer just the feeling of let's take pretty pictures and let's just do mineralogy. What is more science that we can do? So I'm going to go counterclockwise here, though. So mini RF is our mini radio frequency instrument. So it's mostly used for communications, but it has done some minor water ice data as well there. I'm personally on we don't call it DLRE. It's called Diviner, and I'm on the Diviner science team. I'm one of the newest members of the Diviner science team. But the Diviner instrument gives us our temperatures for the moon, and I'll go into why temperatures are very important for studying lunar geology and ice. Crater is our cosmic ray telescope. WAC and NAC are our wide angle camera and narrow angle camera. Gotta love acronyms at this point. LOLA is our laser altimeter, so make sure where all the pretty elevations are. LAMP is our Lyman Alpha mapping project, so it can really tell us where all the cool chemistry is. And then down at the bottom there is LEND. It's our neutron detector, our neutron spectrometer. So with all of these instruments, we can now have a full array of different maps. Again, not just where's the pretty pictures and where's the mineralogy. Now we can really bring in some of the physics and the chemistry involved with a lot of this. The neutrons, specifically with the solar physics people, where's a lot of the radiation that happens on the moon. Sunlight and infrared is, and I don't really deal with ultraviolet. So infrared and sunlight is what I usually flip back and forth to. Where's all the cold spots? Again, I'll have fun with cold spots here in a bit. Elevation, especially if we want to go back to the moon, we got to know where all the dangerous rocky places are, where all the hazards are, and be able to map out where all the smoother landing areas are in that case. A little bit more into the neutron detector though. So all these really pretty blue spots is where we typically see hydrogen. And from that hydrogen, we can then figure out, is it water ice or is it a radiation chemistry just blowing off hydrogen? So that's why the neutron detector is very important for us. So in terms of sunlight, we're now having better, higher resolution of where solar illumination maps are, especially at the South Pole. So this is the South Pole of the moon. So all these really dark areas is truly brings out the phrase where the sun don't shine. So these spots get very, very dark. And this is over a couple of days worth. So these areas of darkness truly do not see the light of day at all. But notice how there's some spots that are just so tiny and yet they're so dark as well. And that actually comes out to be very important for future human exploration as well. So now going into 2013 into present day, there was a little bit of a lull at first, but by 2018, 2019, things are starting to pick up a little bit. Unfortunately, quite a few things got canceled in 2018. 2020, of course, is 2020, so things are kind of like getting pushed back or delayed a little bit here and there, though. But 2019 still worked, at least with the Chang'e 4 and 5 missions from the Chinese. So I want to mention real quick with the Chang'e 4, they had a really interesting experiment happen here. And I applaud them for at least their efforts. But what they had was a little biodome that was presumably vacuum sealed, and it had cotton seeds in it. And so what they did was, it was a lander on the far side of the moon. well, okay, far side of the moon here, it can get pretty cold most of the time. Now, granted, it could still get sunlight, especially when it's new moon time, but most of the time it gets pretty cold there. And so the Changi 4 biodome here, they had the seeds and they took beautiful pictures. It's like, yay, we sprouted cotton on the moon, hooray. The very next day, what happened was that it got so cold for the biodome that it actually cracked a little bit, and all of that coldness of space just rushed in and just killed all the cotton plants. So the attempt was made. Hooray, they got a positive. The unfortunate part was that the vacuum seal of it just could not hold up to those temperatures. And I'm not saying like, oh, for wintertime, negative 32 degrees Fahrenheit. No. I'm talking like negative 200 degrees or worse. So now looking to the future, now you may look at this and go like, wow, that looks a little bare. Well, you'd be right, because there's actually 2 of them missing in this, but it's still a little bare because most of us are still trying to get through more mission concepts going on. And then we have the Artemis program picking up speed very quickly coming up, and I'll talk about Artemis too. But Lunar Trailblazer and Viper are 2 very exciting lunar missions on top of the Artemis programs to look out for. Also coming up real quick is the Luna 27, 28, and 29 from the Roscosmos. Their landing site is around this particular region. This is an elevation map of the moon. You notice though that this whole like dark bluish greenish area, this is the lunar South Pole Aitken Basin. So this basin has caused some really exciting work for us lunar planetary people. So very exciting that Roscosmos is going to be landing within this area to get a sense of the geology and the chemistry, and then we can learn about the physics of what made this basin. So exciting. So Artemis 1, 2, and 3. Artemis 1, it will be uncrewed, an uncrewed flight test of the Space Launch System. So essentially it's going to be our dress rehearsal. Artemis 2 will then be our first crewed flight test of the Space Launch System and Orion, and then onward to number 3, which is planning at this point. But the lunar South Pole can give us so much to look forward to, though. So again, just looking at this pretty picture of the lunar South Pole, you may think like, yeah, okay, there's some like nice craters. Yeah, so what? But looking at the chemistry and the physics, looking at it through a geologist's point of view, how weird some of the craters look is one thing though. But looking at the chemistry, we have something called permanently shadowed regions, or PSRs, which me originally being a radio astronomer, I too worked on pulsars very early on, and so we would abbreviate pulsars as PSRs. And so switching from PSRs of pulsars and then switching to PSRs as permanently shadowed regions really messed with my mind for a couple months. And I think I'm just now getting used to it, thinking PSRs of the moon instead of pulsars in space. But these permanently shadowed regions, what I just showed a few slides earlier with the lack of solar illumination within these craters, these are the craters that we would have some sort of water ice signatures. Now, whether they're on the surface or are they deep down below, that is still being determined. Right now, that's still kind of low resolution because you saw how tiny some of those really dark spots were on the moon. But knowing where's the water ice, follow the water, really fascinating regions. And this is just the South Pole of the moon. Now, when I show this picture, whether you think the moon to be just a large cheese ball at this point or the moon is on fire, don't worry, it's not. But these are just some of the temperature maps that I typically work with a diviner instrument. So obviously color scale here though. So the oranges and reds are typically 200 Kelvin. I have to work in Kelvin here. And then the really pretty dark blue areas are down to about 40 to 30 Kelvin. So we're talking negative 400, negative 350 degrees Fahrenheit in a lot of these bluer areas. So pretty cool. And so what I just showed with the orange, this is during the day and then during the night. So you start to see how cold a lot of these PSRs remain, and then how cold or how some of the heat retention is in some of the crater rims here. So very exciting. And it's not just water ice. Surprise. So again, looking at a diviner diagram here, and where L cross impacted off to the side here to confirm that there was water ice. But now looking at the different kinds of temperatures that we see here, there's our Kelvin scale here. Particular attention here is that now we have to be careful of what kind of ice we're dealing with. This is a potential hazard for our next crewed space flights. So now we're dealing with potential frozen sulfur. We're dealing with sulfur dioxides and hydrogen sulfides and ammonias. And so they're very corrosive. Now, are they everywhere on the moon? No. Are they in large quantities that it's going to be very detrimental? Probably not. But if we're wanting to core these ice samples in large quantities, we're going to have to be very careful on how we use our instruments and make sure that they're not going to corrode quickly, especially if there's ammonia and hydrogen sulfide, because those as vapors, you don't want to mess with them either. So Artemis is going to be a fantastic and fun journey for our next, gateway into lunar science and human exploration. Again, we haven't been to the moon in what, 47, 48 years now. So it's been a ride. Like I said earlier, there are two also exciting missions along with Artemis. We have a Lunar Trailblazer as part of Simplex. So Simplex is just kind of an interesting competitive mission concept, and Trailblazer was the winner. That is led by Bethany Ellman out at Caltech. And then we have the Viper mission. So the Viper science team is still being formulated at this point, though, but Viper is going to have a drill system also at the lunar South Pole. And the drill is going to really give us a sense of how's the soil behaving at those cold temperatures. And it's also going to have a spectrometer too. So spectrometer is going to give us the chemistry, the mineralogy, what kind of ices are we dealing with versus what kind of rock are we dealing with. A very fun article. I obviously haven't been able to screenshot the entire article, but I highly recommend you to read this fantastic article that we're still exploring a lot of the, oh dear, hang on, my computer froze a little bit. Unopened Apollo samples to get us ready for the Artemis missions. And so these were very, very carefully opened because we haven't dealt with Apollo samples in such a long time. So a fantastic group got funding. This is part of the ANXA, NASA's Apollo Next Generation Sample Analysis Group. Now, some of you might be going, oh goodness, this might be the setup of like a B-rated sci-fi movie and space worms are going to come out of the samples and everything. We got to be careful for our own health and the Earth. But then also we need to be careful with the moon as well. If we're wanting to bring instruments to the moon again, we need to make sure we don't contaminate the moon whatsoever. Oh dear. Well, there we go. So the planetary science community of just going like, oh no, you're right, we shouldn't have to contaminate ourselves, and vice versa with the moon. So this is just one of many efforts going around with planetary protection systems under NASA. It's a fairly new branch. It's been around for a couple of years now, though. But I'm happy to be a member of the astrobiology at Goddard Space Flight Center. So it's a fantastic group. It's fairly new. I don't think we may have just hit our 1-year mark, so we're a very new group. But part of our initiative is to make sure that we're handling any samples brought back from the moon, asteroids, anything, anywhere, that we're being very cautious and very safe. And what kind of precautions can we take with our own health and safety, and also with instrument safety? Make sure our instruments are clean and stable enough to handle samples, to not only work on the moon and Mars and asteroids and whatnot, but also to bring them back safely and make sure we don't melt our ice cores from the moon on the way home, because that would be sad. I would be sad. That would be heartbreaking. So just to wrap up, there's some fantastic lunar resources out there that I highly encourage you. If you're really into lunar science, but you want to just learn more, just like snippets of the moon, this is quickly wrapping up, hopefully, fingers crossed, by the end of the year. This is the Encyclopedia of Lunar Science by Springer. It's coming together very, very nicely. I'm one of the co-editors of this encyclopedia. But then here is some lovely links that I will leave up here for the time being. Let's see, what all do we have here? Yeah, okay, so any updates about Artemis? Here, quickmap.lrock.asu.edu. So QuickMap is a really fun tool, very free to use. It's almost like Google Earth, but for the moon. It's very, very fun. But what you can do is that you can see the moon 3D level, and you can go through a scroll bar and see all the different kinds of lunar data. For yourself, you can explore lunar data on your own. Maybe you'll discover something interesting too. LPI, like I said, brings about a lot of the updates on lunar missions, and then all the lunar samples. And then finally, oh dear, well, there goes my computer. And finally, the astrobiology. I just lost a cord. It just went pop out of my computer. So everything's fine. The astrobiology link is there too. But happy to answer any questions that you find folks may have. But thank you so much, Astronomical League, for having me on today. And hope you enjoyed the lunar science roller coaster. Thank you.
Thank you, Caitlin. Scott, have we got any questions, or does anybody here have any questions?
Well, let's take a look here.
I have one while Scott's looking, if you want to.
Sure.
Take your time.
Sure.
Caitlin, I've read something about water molecules being heated and bouncing along the surface of the moon, seeking out, well, not seeking, but finding cooler areas on the surface. Can you elucidate on that a little bit for us?
Yes, so us lunar people have to talk to heliophysics people quite often, and we typically don't talk the same language whatsoever. So it can get very entertaining during virtual conferences. But what's going on is that we have to pay attention to solar radiation. It's pretty much heating these ices, these volatiles, and they're sputtering outward. That's the fancy science term here, the sputtering. So all of those ions, all the hydrogen and oxygen being torn apart and then skipping along, and they got to find the cold place somewhere. Sometimes if there's not a cold place, sometimes it could actually just kind of sink into the regolith, but that typically doesn't happen, or at least not at the poles. At the poles, it's very easy to find any kind of little cold place there. So the map that I showed earlier with PSRs, they're typically large areas, but very recently we're realizing that there could be cold spots centimeters across. And with that kind of resolution with an orbiter, we just don't have it. So there could be centimeter little pock marks on the moon where all those volatiles can just kind of creep in and freeze up.
Has any water been detected nowhere close to PSRs, like the equatorial regions of the moon, for example, in the red
Yes,
line?
yes, actually, there's a postdoc also here at Goddard named Dr. Casey Hannibal. Casey is amazing. She wrote a proposal and got to use the Sophia telescope. So for those of you who don't know, Sophia is a fantastic infrared astronomical telescope on board a very large plane, a 747. Just it's amazing technology, and it's wild to watch YouTube videos of how this is all rigged up and everything. But her sole purpose though was to get certain infrared signatures of the moon, and she had confirmed some water signature at the equatorial region of the moon. Now, whether it's solidified or it's vapor, and what's the physics going on here, stay tuned, because that's exactly what she's working on still.
You might want to take yourself off of share at some point so we can see it. There we go.
Hi.
Scott.
Yeah, there's a question here from a solar system ambassador. Okay.
Hey, yay,
yeah,
fellow
that's right.
solar system ambassador.
That's right. So Gregory Shanos, who's watching on YouTube, he says, Dr. Ahrens, when giving a public lecture on the moon, how do you handle someone who still doesn't believe that we ever landed on the moon?
Oh dear. You know, we're in a virtual world. It's much easier to mute people. But no, I've had the interesting adventure of meeting certain realms of people at public lectures and conferences before 2020. In which case it's all about listening, because they if anything, they want to talk. And so I have X amount of patience to listen though, but you pretty much just kind of go like, okay, you know what? Thank you for attending. Thank you for listening to my presentation. Have a good day. Because they took the time out of their day to come listen to you. Now, afterwards, they want to hear themselves talk. Okay. But thank you for coming to my talk. Have a nice day. Bye.
Yep. Okay. All right. So
tell us about the Mercury 13 pin.
You noticed that.
I did.
Yes.
Ah,
I actually just got that in the mail yesterday. I'm very happy, and I'm wearing the commemorative virtual ALCon pin as well. So, but yes, the Mercury 13 pin. So we were a group of us on Twitter were celebrating Wally Funk. And the whole Mercury 13 concept, where these fantastic women of NASA were preparing to be astronauts, and they just never got the chance to fly. And so the fantastic voyage of Wally Funk very recently. Hard to believe that was just a couple weeks ago. Yeah. It still feels like yesterday at this point, but time is weird in a pandemic world right now. But a few of us who celebrated Wally Funk's recent flight all got we got Mercury 13 pins, which you can get now too out of here we go, out of Launch Pins. Go check them out. They now have the Mercury 13 symbol pin available for everybody.
Okay. Oh, thank you. Bob, did you have a question for Caitlin?
Yeah, just wanted to say that first, LCROSS is Lunar Crater Observation Sensing Satellite.
Thank you.
And the problem with people on the moon, the spacesuit problem with the dust, when I talked with Harrison Schmitt, by the time of the third EVA, when were getting ready to go out, they couldn't get the gloves and things to become airtight because of the dust sticking to the rubber seals. The lunar dust is so sharp, it doesn't get rounded like on Earth, when it blows and stuff and little edges break off. And that was a real problem that they had. I remember several years ago, they were selling the name patch off of Jim Irwin's backpack, and it was covered in lunar dust because remember the fenders had come off the rover and threw dust everywhere. So his backpack was all dusted. The little patch with just his name on it, they sold for $75,000, and it was covered in lunar dust. So somebody owns a whole bunch of moon dust because it stuck to it and they couldn't get it clean. So they had to sell it with the dust. So that's going to be a problem. And if they put any equipment, like a telescope, of the dust getting into bearings and things, it's all razor sharp chunks of little rock. And they find out when they're examining rocks in the Johnson Space Center that all this stuff is very sharp, these little chunks of rock. And you can agree, I see Caitlin nodding her head. She knows that these rocks are not rounded like Earth dust. So that's what I have to say. Thank you very much for your talk. I enjoyed it. I do cover all the space flights in Luna Cognita. It took me a while to put a table together of everything because the Soviets were secret until the Soviet Union collapsed. And then we found out all of their failed attempts and whatnot. And so I cover all that as well.
Oh, I need to get your books. I really do. I'm still fairly new to the lunar community.
Yeah, watch out when you go to pick it up. It weighs 15 pounds altogether.
Hey, you know what? Volumes. I mean, well, my phone is on a volcanic textbook, so I understand. I understand weight because I work on space volcanoes. Yep. Yeah. I understand.
The reason it's in 3 volumes, Springer can only print 1,200 pages at a time, so they had to divide the book up.
Yes, I'm currently working with Springer, so I understand Springer's ins and outs. But I love Springer; they're wonderful.
They're
wonderful
doing a great job. Yes, they are. Thank you very much for your talk.
Thank you.
Have you got anything, Scott?
Yeah, Texas backyard astronomer Glenn out of Glen Rose, Texas, watching on YouTube, asked, is anyone planning on targeting the moon nonstop during the Artemis mission?
Targeting nonstop.
Yeah, I think that maybe the question is because they're planning the Gateway, lunar.
Oh, gotcha. Yeah, well, as long as the dress rehearsal works fine with Artemis 1, we may end up seeing what happened between late 50s to early 70s with that huge boom of more landers and orbiters. Now, granted, we're coming into the age of private space companies now as well. Certain competitive missions like Simplex. We also have something called the CLIPS program as well under NASA. We're starting to build a whole regime of not big, broad, let's put all the instruments on these orbiters, but instead smaller, compact missions and even CubeSats. For those of you who don't know, CubeSats are these couple centimeter by couple centimeter cubes with little tiny microscopic instruments, though, satellites per se, but we're hoping to do maybe some CubeSats at the moon as well.
Oh,
so
cool.
All of these smaller competitive instruments, I can definitely see a larger boom coming up with that hopefully soon. That would be very exciting.
If you have a question about Mars, John Roberts is asking, watching on YouTube, this is a question about Mars, but also about dust. Do you have any thoughts on the first core drilled by Perseverance, the core which became dust? Do you think we'll have better luck next time?
Oh my goodness. Well, I honestly think that's going to be a better question for Dr. Larry Crumpler.
Okay.
Who thankfully just signed on.
Yep. John asked that question again. Okay.
Yes.
All right. Well, I think that's pretty much it.
Yeah, I don't want to spoil
many
anything
nice
about
compliments about your.
perseverance.
What's that?
I don't want to spoil anything about perseverance, and I'll leave it to Larry. So.
Yeah. Okay.
I will add that Caitlin does a lot of work with ICEs. I think it was mentioned by Terry during the introduction that she simulates in the lab ICEs found on Pluto and other bodies. And you might, we'd love to have you back sometime to talk about that.
I'd love to come back.
Yeah.
Thank you. Yeah.
We've got live events coming up.
Yes, we do.
Awesome. Well, thank you so much again for having me.
Thank you,
Thank
Caitlin.
you, Caitlin. It's always a pleasure. Chuck, do you want to take over?
Yes, we have an award to give out. This is the 2021 Sketching Award. And let's see, is Michael Rosalina here?
Here I am.
Okay,
Right
there you
here.
are. How are you? We are.
I'm good.
Let me show you.
Hi, Caitlin.
Hi, Mike.
Oh, that's right. You know
Good
each
to
other.
see you.
Yeah.
Yeah, we know each other through StarQuest. Woo.
Okay, this is, I'm going to share screen here for a moment. Okay, this is, oops. Can you describe this for us?
Sure. That's my 12 by 16 roll-off roof observatory. It's in Greenbrier County, West Virginia, which is in the mountains. I'm in a very rural spot with dark skies. Generally, my skies are 21.45 to 21.75 magnitudes per square arc second. If you use a SQM meter.
That's excellent.
That
Yes,
scope is a C14, a Celestron, pardon me?
that's excellent.
The Celestron, yeah, that's a C14. I do mostly visual observing and sketching. So my observatory has a work table and an easel and chairs and workspaces, and all my media is real handy. So it's nice to have. The observatory is the best accessory an amateur astronomer can have.
Okay. The sketches are of the pup, a Sirius B, and they didn't copy here as well as the beautifully feathered brightness on the original diagrams, but if you would describe it for us.
Put all the animals were done playing, it keeps them all safe.
Michael?
Yep. Yes. Yeah, right now is the best time to see, try to see Sirius B, because it's at its greatest separation from now till about 2025. And but it's only about 10 arc seconds. This was my third attempt to see it. You have to have pretty good seeing. The first two times I didn't have very good seeing. And Sirius A is about 10,000 times brighter than Sirius B. So it's, it's something where you have to pick your time and pick a good night. I tried using an occulting eyepiece that I had made, but Sirius was just way too bright. And so I ended up putting Sirius A out of the edge of the field of view, and you can just see it down there at the bottom. It's the diffraction spikes. And once I did that, though, once I put Sirius A out of the field of view, Sirius B popped in between the diffraction spikes, which you can see. The sketch on the right is just, I inverted my original pencil sketch, which is on the left, just to give you an idea of what the view looked like through the observatory, through the eyepiece.
Fantastic. I know it's a tough catch. I've seen it, but it wasn't easy. Okay, there you are again. Do you have your plaque handy?
Yes.
We'd like to encourage other people who sketch. Beautiful. We've had, I can tell you, could we mute? We've got somebody's sound on in the background. Okay. Michael, can you say something so we can get you back on the screen here?
Yes.
Yeah.
Yes. What I want to say is I want to thank the Astronomical League for this award and also for encouraging amateur astronomers to sketch. I think that sketching is the best way to improve your observing skills, and it leaves you with a visual record of your observation, as well as a chance to exercise your creativity. So thank you once again.
I've done about 3,000 sketches in all of my programs, so I couldn't agree with you more. It makes you a critical observer, makes you seek out detail that you might not notice otherwise. Thank you so much for joining us, and congratulations again. And I envy your skies.
Okay,
take care.
Okay, thanks. Bye.
Thank you. Okay, Terry. Jim. And there we go. Okay. Okay.
Our next speaker will be Dr. Larry Crumpler. The title of his talk is Perseverance Mission, What We Have Seen, What We Are Doing Now, and Where We Are Going. Dr. Larry Crumpler is currently research curator of volcanology and space science at the New Mexico Museum of Natural History and Science. He is also a member of the Mars 2020 Perseverance team and Ingenuity helicopter science, using the rover like a remote field geologist to map the geology along the rover's traverse. He is a field geologist and has been on many Mars missions, including Spirit and Opportunity, Mars Reconnaissance Orbiter HiRISE camera, Magellan, Viking, and exploring Mars since before the first flyby by Mariner 4 in 1965. He is the author of a book about Mars called Missions to Mars that will be coming out in the fall of 2021. So Dr. Crumpler, welcome, and I will turn this over to you.
Thank you, Terry. Can you hear me?
Yes, I can.
All right, good. So yes, so I'm a longtime Martian. Before that, of course, I was an amateur astronomer and looking at Mars with a telescope. And of course, I only had about a 2.4-inch telescope. So that meant that about all I could see on a really clear night was maybe the polar caps. And I can imagine that I could see dark markings. But otherwise, I didn't get my first good view of Mars until we started sending spacecraft there. So what I'm going to do is start my presentation. And it's going to be a presentation that's mainly, well, when you talk about these missions, it tends to become a story. And it's a story about, how you start out and where you go and what you're doing today. And it tends to develop along a timeline, and the timeline is the traverse. So that's what I'm going to do. And I hope it's not too boring for everybody, but along the way, we'll see some wonderful images. And as a final caveat, I'd like to say that, on these missions, when they're active, we have a rules of the road, which means that team members can't talk about things that have been released and aren't really the spokesman for the mission. So we're not allowed to really show things, which I'm thoroughly going to violate in many cases with this presentation. So it's all in the interest of presenting to the public. So anything you hear, you must immediately forget and rely only on NASA for the final official word, okay? Okay, so I'm going to start sharing my screen and sharing my presentation. So this is again a presentation about the Perseverance mission on Mars, and basically it is now approaching Sol 180, that is 180 days, Mars days or sols on Mars. And I'm going to step through from landing to the present. So let's get started because I have a long ways to go and I'll probably try to run over time. This is Mars over the ages. Before we sent spacecraft to Mars, of course, we had the view over here on the right, telescopic views, about all we could see. And this is a particularly good image. I think this might be a Hubble. I've forgotten already. And most of us had the less clear viewing through the atmosphere. And of course, all we could see were dark blotches, the reddish color of the bright areas, and maybe the polar caps. And of course, early observers imagined that they could see all sorts of linear features, as in this image here in the center of the screen. And in fact, this was the view of Mars we had right up until 1962, when that particular image on the right was published in a map by the U.S. Air Force, who was responsible for making maps of celestial bodies up to that point. And so it was pretty much the view that we had with a lot of observers since the beginning of the 20th century. So, and then of course, as missions progressed, over on the left is the sort of the view we have of Mars today, a very dynamic planet with lots of interesting landforms, and behind those landforms are a lot of interesting geology and a very complex history. And of course, on the far left here are the images that we are, now looking at on the surface of Mars. No longer are we looking at, 100-kilometer wide features and blotches, but we're actually down at the granular level looking at individual grains of minerals in the rocks, roving over the surface and looking down from orbit with images from instruments like the Mars Reconnaissance Orbiter high-rise camera that look for all the world like air photos. And of course, the way we got here, of course, is by sending lots of missions, beginning in 64 with the Mariner 4 flyby in 1965. I was one of the kids sitting there by the radio waiting to hear the results. Of course, in those days, we didn't have a lot of public interest in missions. There were other things going on, and there wasn't a lot of news releases about it. But eventually, the information trickled out that Mars was, a cratered and dead planet. And of course, later on with Mariner 9, in the beginning of the 70s, we actually learned that Mars was the place that we're familiar with today. Lots of interesting landforms and whatnot. And then, of course, we had Viking in the mid 70s. We actually sent a spacecraft down to the surface, two spacecraft, the Viking 1 and 2 landers. And of course, we got our first real close looks at Mars. It was first successful landing on Mars. Then on to, there was basically a 20-year gap from the late 70s to the late 90s before we got back to Mars again. And so during all that period of time, we were really developing our knowledge based on global data we had collected with the Viking orbiters. And then we went back to Mars with Mars Global Surveyor in 1997. And at about the same time, we had sent the Sojourner rover to the surface, a little microwave oven-sized rover that tested out the idea that we could actually operate spacecraft on the surface of the planet. And then, of course, we followed through with more complex orbital missions. That was sort of the end of the exploratory phase of Mars. Then we went into sort of the investigation phase with Mars Odyssey, 2001. Then, of course, Mars Reconnaissance Orbiter in 2005. And at the same time, we sent the Spirit and Opportunity rovers, which landed in 2004 and operated for 14 years. And that's where we really learned what Mars is really like. And we learned a lot of new questions that we needed to ask in order to understand it better. And of course, there was Phoenix, which landed closer to the poles and the high latitudes of Mars. And then we had the landing of the Curiosity rover, much bigger and much more capable instruments in 2012. And of course, at that time, we also sent the MAVEN spacecraft to Mars, which is tasked with understanding the atmosphere and the climate history of Mars from the atmospheric chemistry. And then, of course, We had the InSight lander, which is investigating Mars quakes and understanding the interior of Mars. And then finally, in 2020, we sent Perseverance to Mars with the even more complicated instruments and a even greater list of tasks. And this is all precursor to samples that Perseverance will collect that will be returned sometime in the end of this decade by hopefully a Mars sample return mission. But anyway, today we're going to talk about Perseverance. So let's get on with that. So here's a little sort of summary of what we have on the Perseverance rover. It's very similar to Curiosity rover that landed in 2012, at least in scale, but it has a lot of different instruments, many of which are upgraded from previously. These include things like the Mastcam Z, which is the high resolution color camera. It has a normal focal length lenses as well as 110 millimeter telescopic sort of perspective lenses that we use quite a bit on this mission. SuperCam is the laser zapper, which zaps rocks in order to understand their composition. But it also has a camera associated with it. We can use like a telescope to zoom out into the horizon and see things at great distances. And I'll show you an example of that. It also has a microphone that we've used to listen to some interesting sounds on Mars, of the rover driving, of the helicopter, and so on. Then, of course, we have the META, the weather station, which is this little mast that sticks out on the edge of the vertical mast here. Of course, measuring all of the characteristics, temperature, humidity, and so on. And then, of course, we have the long arm with a series of complex instruments on the end that are upgraded from the ones that we had on Curiosity. We have one instrument called Sherlock, which has an ultraviolet spectrometer, which is good at looking at for organic compounds. And that'll be very useful as we get into looking at some of the sediments that are down the road here. Also part of that investigation is Watson, which is a high-resolution hand lens-like camera that we can look at rocks up close, as well as take images of the surface at a great distance. So we use that frequently to take, these beautiful selfies of the rover. On the other side of the instrument package is an instrument called Pixel, which is basically the instrument we use to analyze the chemical composition of rocks in extreme detail. And we can investigate individual crystals as well as investigate the entire surface of a rock with this instrument. So it's a very powerful tool for understanding what we're looking at when we look at these rocks up close with, for instance, with Watson or Sherlock. And then, of course, last but not least, on this end of the arm is a drill, which we'll use to collect samples from rocks on the surface and then return them to a device over here which collects those as core tubes and then sends them to an internal lazy Susan sort of arrangement, which stores them inside the rover for later deposit on the surface for later return by a future mission. Of course, we have a couple of technology instruments. One is MOXIE, which produces oxygen from the Martian carbon dioxide. We've already tested that and it works wonderfully. And of course, the Ingenuity helicopter, which is testing the idea that we can actually do powered flight on Mars. And it's turned out to be way more successful than we even had hoped for. And we'll see lots about that in a second. And then finally, there's another instrument called RIMFAX, which is basically it's a ground penetrating radar, which looks down into the ground as the rover's driving along and gives us a sense of what's underneath the rover in the rocks in the substrate up to tens of meters below the surface. This is a tool that you'd love to have in the field, trying to understand what you're walking over. So that's kind of a summary of what's going on. And the goals of the mission, of course, are with all these instruments, none of this is very useful unless you understand the context. So a big goal is to understand what we're actually seeing, the geologic context of the landing site, and what the history of the rocks were. And of course, the really big goal is essentially astrobiology. That's where we're actually trying to understand the past presence of life, rather than not only just whether it was actually habitable, whether there was actually microbes that had existed at one time in the early wet history of Mars. And so we have all the tools for detecting that if possible. And of course, we also are preparing for humans on Mars with test technologies like the MOXIE oxygen generation tool. And of course, the helicopter itself is designed to basically understand whether we can use such tools for exploring around traverses by future astronauts on the surface of Mars. But really, the big goal of the mission is to cache samples, up to 30 or 35 samples that we will collect at important locations that we document very carefully in all sorts of ways. And then we'll store them on the rover for a deposit on the surface and eventual return. And the way that works is, like as shown here, we have the Perseverance rover actually collects the samples, and at some point it actually drops them on the surface. They're in these sealed tubes that are perfectly sealed against any sort of contamination or heat or cold, and we leave them on the surface. They're later retrieved by a rover towards the end of this decade. Hopefully we'll send a rover that goes and collects those samples. It then returns them to an ascent vehicle, which sends them into orbit. It rendezvous with a return orbiter and sends them back to Earth, where we receive the samples back on Earth. And we have a bunch of tubes on board that are ready to go, plus a bunch of blanks for the calibration purposes. And so that leaves us with about 38 samples, and we hope to at least have 20, usually multiples of each target. So where did we go? We went to a place here on this hemisphere of Mars, at a place in the northwestern corner of Isidis Planitia, which is a large ancient impact basin which is almost thoroughly eroded away. It's on the edge of the highlands of Mars and the lowlands, and it's in a place called Jezero Crater. We'll look at that closely in a second. There are several other dots on here which are previous landers or existing landers. Here's where the Curiosity rover landed in Gale Crater in 2012, down here in the lower right. Above that slightly is where the InSight seismic instrument package was landed on the surface in 2018. It's operating successfully and has told us a lot about the inside of Mars that we just didn't know before. And then, of course, the Chinese rover Zhurong, which is part of the Taiwan-1 mission to Mars, landed in May and is currently operating and just celebrated its 90th sol on the surface of Mars, a successful mission so far. And of course, on here also is where the European Space Agency landed the Beagle lander on Mars in 2003. Unsuccessful. It actually successfully landed, but just didn't deploy the antennas properly. So anyway, that's this hemisphere of Mars. So let's go to Jezero Crater. So this is where we went. So it's about 50 kilometers across, almost 30 miles across. And we landed here not too far from the western edge of the crater. And if we look at this box here, I've shown over here on the right the same scale box on familiar Earth features. For my local audience, I always show it surrounding Albuquerque, New Mexico. So it basically completely encompasses New Mexico. So this whole area, the whole area of the city of Albuquerque. And here, of course, more familiar to everyone, Washington, D.C. So it's a fairly large area. And so we're driving, hopefully up across this area towards the western rim of the crater, which would basically be like driving halfway across town. Zooming in a little bit, here's the image we were just looking at. Here's the box. So here's the blow up of that box. So this is where we landed out here about a kilometer away from the edge of the delta. And the delta is what we went here for. It's basically a place where a large river enters the western edge of the Jezero crater. And when rivers enter a large body of water and they're carrying lots of sediment, the water slows down and it deposits all those sediments in the form of what we call a delta. For instance, the Nile River Delta or the Mississippi River Delta. Lots of fine grain, low energy muds that are just laid down and perfect for preserving things. In fact, a lot of the fossil environments on the Earth are precisely that sort of environment. So it seemed like a good place to basically do this mission because we have potential for preserving things that are now exposed through erosion, and we can investigate whether they ever contained microbial life at the very least by looking at the rocks in detail. So this is where we landed. So now we're going to look at a little bit about landing day. Over on the right, the Mars Reconnaissance Orbiter high-rise camera captured this beautiful image of the rover on its parachute coming in. So this only took place over a space of several minutes, so it was precise timing and positioning at the orbit in order to capture this image. And shortly after that image was taken, the rover dropped away from the parachute and went into powered flight using its rocket packs. And it used a new system for this mission, which was called terrain relative navigation, where it actually was able to select a safe landing site rather than just land wherever it happened to end up. And so there it is coming in, and shortly after we went in powered flight. And of course, by now you've probably seen the image where as we come in for landing, the rover unreels on cables. And this time, we actually had cameras on board capturing that in detail. And there's beautiful movies of this happening with the rocket blast blowing all the dust away from the surface on either side of the rover and the rover swinging underneath on the cables. And of course, the rover had a camera on the back of it looking up, taking a movie of the lander itself. And of course, this is the view we got of that. So this is it hovering over the rover just instance before the cable was cut and it flew away as shown here. You can see the slack cable here, bits of dirt flying all over the place. And of course, that flew away and landed elsewhere, or crashed actually. And the rover was successfully on the surface. So this is the landing site. There's the delta margin way out there in the distance, about a kilometer away again. Over here is the rim of Jezero crater. So you can see it's a big crater with a high wall. So it's essentially a ring of mountains around this flat floored plain filled with a delta and then filled with what appear to be volcanic rocks that have come in after the delta. And so we landed out here, and you can see the terrain relative navigation picked a perfectly boring place to land. Very flat, the usual dunes, a few rocks here and there, and of course you can see the blast marks here where we blew all the dust off of some of the local outcrops. Immediately after landing, we undertook, to do, investigation of the surroundings, and followed that by efforts to set up for deployment of the helicopter. We needed to get the helicopter off from underneath the belly of the rover quickly enough so that it could deploy its solar panels, which it's powered by, and successfully survive on the surface of the Mars. So we drove over, dropped off a dust shield out of the way of the potential future flight of the helicopter. And then we drove off to the north and got a selfie. Here's the helicopter hanging just before deployment to the surface. We drove off to the surface and got this beautiful selfie of the rover on the surface of Mars. There's the rim of Jezero crater and the delta in the background. Here's Ingenuity helicopter sitting on the surface ready to go. And of course, you can see the blast marks from the landing and the terrain around the rover. And then we drove off to the east to witness the first attempts at flight. And so this is the view from the nav cam. This isn't the mass cam. This is we have navigation cameras that are very similar to the mast cam and the location on the mast, but a little bit lower resolution, so they're easier to get that data back and take panoramas on a regular basis. And they have kind of a wide angle effect, so things look pretty far away, but there's the helicopter sitting off there. But of course, mast cam, you can zoom in, and so this is the helicopter sitting on the surface on Sol 55, ready to go, just before. And then basically we did movies of each attempted flights. And of course, this is one of the first flights, the third flight in this case, where we're actually looking down at the surface with the color camera at the place where we took off. Here's the helicopter shadow. There's the feet. Here's one of the feet in the field of view of the camera here. And basically, we flew the helicopter back and forth a couple of times here before getting more ambitious. But during one of these earlier flights, taking these color cameras, we actually got an image of the rover sitting out in the distance. And you can actually see it there. You're kind of looking at it. This is the rear end of the rover. It's kind of looking over its shoulder at the flight. Actually, in this case, filming a movie of the flight during these first few stalls of powered flight on Mars. And this is a movie that Mastcam Z made of the helicopter flying on the surface of Mars. So there you can see it actually works. It flies in the thin atmosphere of Mars by spinning blades a lot faster than Earth helicopters and having larger blades. And it's executing the exercise that I've shown here in the still image, where it flew out to a new location south of the landing site, picked its own location, and landed in a place it had never been before. And so that was the beginning of a series of more ambitious flights. In the background, by the way, is Jezero Crater Rim again. Here's a smaller crater rim here that eventually we drove down here past this first landing site and around the other side of this small impact crater over here on the left. And the helicopter preceded us along the way as it flew south. So I'm going to interrupt the story about the helicopter here, tell you why the helicopter is flying to the south here. So here's where we landed, and here's where we've been driving, and here's where we are today. And the delta, of course, is up here in the upper left. So what the heck's going on? Why aren't we just going to the delta? That's the purpose of the mission, right? Well, it turns out that the mission's very complicated. We have some instruments that have to be kind of started up, checked out, proved out, and there's so many and they're so complicated that we have to take several months to get all of them operating. And we want to make sure they're all operating before we actually undertake the purpose of the mission. And so we drove to the south also because we want to understand what it is we landed on here. It's obviously a different terrain here to the right of where we landed than to the left. And the delta is obviously something totally different. So this looks from orbital mapping to be a much younger surface than all of this, even though it has more craters. We suspect that's because it's retaining craters because it's something more like a lava flow. And so we wanted to get a sample of that, but here's the problem. The sample package wasn't going to be ready for doing its job for several months. So we were sort of stalling for time in one sense, but also we wanted to understand the nature of this contact so that we get a better understanding of the overall context of the geology for the mission as a whole. So we drove to the south, and these little green dots are where the helicopter proceeded in front of the rover and landed successfully. It's now actually way out here. And so it hopped along in front of us as we were driving along. So it kept photo bombing our panoramas as we would drive by. There would be the helicopter. We'd go to the next, there's the helicopter sitting there, the next place, helicopter. But it would then move on, and we would basically arrive and pass it, and then it would fly again. So I'm going to show you, I think, this is kind of the whole scenario for what we're going to do. We're going to go to the south, and then eventually we'll turn around and we'll come all the way back. And we can't cross this area because it's very rugged. It's badlands. So we're going to actually go all the way around it and come up here, and somewhere this fall, probably November, December, we'll be driving along close to the delta, hopefully arriving at a place where we'll start at the ascent of the delta somewhere in February of 2022. So that's the plan. And so right now we're down here, and we're going to do a little jog out into this Badlands to try to understand it, because it's clearly something even older than what we are have been driving on. So we're going to do that, and then we're going to turn around. So now we'll get back to the helicopter. So here are the images that the helicopter has taken as it's flown along this over the surface. And the green dots again are where it's landed. So we have a nav cam looking straight down from the helicopter that takes these black and white images. And then the color images that we saw the rover and the landing site in previously. And it takes a series of these periodically as it flies along, and they're higher resolution and give us a little bit better perspective of the surface. So anyway, so one of the flights, it flew all the way from this location all the way across the Badlands to a completely new place that had never been, and picked the landing site and landed down here, taking these images along the way. And so this image then over here on the right is this image. And what I've done is, this is the actual helicopter image on the left here, and I've placed in it a model of the rover as it was positioned when it was at this location, because the rover had already moved on when the helicopter flew over this area. But you can see our tracks here, you can see individual rocks, so you get a sense of the level of detail we have. And then as it flew out across here, it got beautiful images of the Badlands. And here's the navigation camera movie as it took off from this location. And you can see how it works. It's going up to altitude here. And now it's going to start flying to the south and west. Here are the rover tracks coming into view. Now it's going to go to the edge. There's kind of an escarpment here next to the Badlands, which start with the dunes here. The helicopter's stopping here to kind of get its bearings, kind of get a sense of, the terrain really well, because now it might have to come back here, and it wants to be able to identify this location. So it's flying out across the dunes on a flight across unnavigatable terrain. So it's out here all by itself in the middle of these Badlands, and it's going to fly all the way across to the other shore, as it were, over on the other side. So anyway, that's a typical NavCam flying movie. And this is one of the color frames during that flight across those Badlands. And so this gives you a sense of what it's like to fly over the surface of Mars. In this case, probably about 15 meters above the surface of Mars. Rim of Jezero crater in the background. Here's a small remnant of the delta sitting out there. And the rover is now over here on this escarpment. And this is where the helicopter flew on this particular flight. So here's where it arrived at the other side. There's the escarpment down here where it actually took this image right here. And of course, we're sitting right here a couple of days ago. We actually just drove across this image with the rover just this past week. And we're now sitting up here to the north. And during one of the flights, the subsequent flights, we actually were doing a jog to the north and west. We actually got another one of those color camera images looking out across the Badlands here to where the rover was sitting at the time, over here at the very bottom of our V-shaped traverse. And you can actually see the rover sitting way out there. There it is again. And altogether, we have something like 5, I think, images of the rover from the helicopter to date. So anyway, the helicopter flew out here, and then this was the 11th flight. Then subsequently, just this past week, we flew out with the helicopter across to this region where the rover will be going in the next few weeks, a month, but to investigate what the nature of this Badlands is before we turn around and start our way back. So what else have we been doing? We have the super cam that I mentioned, which is kind of like a telescopic camera attached to the the laser zapper that can actually look off in the distance and take these kind of telescopic circular views in the distance. And this is about 1 kilometer away. And we can mosaic these and make beautiful high resolution images of things that are far away. So let's look at this up close. So here's the image up close, 1 kilometer away. And we're looking at the edge of the delta. We can see individual rocks, probably fist-sized rocks in the sediments there. So we'll be using that a lot during this mission to examine outcrops. Of course, the Mastcam-Z has a telephoto 110 millimeter lens, and so we use that to look in the distance. Here's a beautiful mesa of eroded sediments, looks like something here in the southwestern US. And so everybody's really excited to get up close and look at these, as well as just the scenic panoramas associated with them. In the background, the mountains rising in the distance, of course, are the rim of Jezero crater, which gives you an idea of the terrain we will be crossing eventually as we climb the delta. In the foreground is that Badlands. And, another thing that happens is we take these panoramas and at the end of them every day, and frequently dust devils photobomb our panoramas. I mean, there's just a very dusty place. And here's some movies that we actually took of some of the dust devils you can see blowing across the surface of Mars. At any time you take a picture, you're probably going to get a dust devil in it if it's sometime in the afternoon. So they're just like Earth dust devils. They are the same size, same scale, just a thinner atmosphere and finer grained material. Speaking of photobomb, we took this image just a couple of days ago. It's an atmospheric observation, a cloud movie, and if you could see this in high resolution, you might actually see sort of bands marching across the sky here. This is a cloud movie. We like to take images periodically to monitor, what the ice crystals are doing in the upper atmosphere. And in this case, the Martian moon Deimos was actually in the field of view. So yet another photobomb by a Martian object moving into our field of view. Yeah, and so captive audience, I have to tell you about what my part of the mission is. I'm doing a thing called in situ field geologic context mapping, or GXM. And the idea is that when you're walking around looking at rocks here on the surface of the Earth, you can kind of identify things by touching them where you're standing, and then you look off to the side and you can identify the same rocks around you. And so you can map them out, the different rock types. And so you end up with these colorful geologic maps which show the different types of rocks around you. So basically that's what I'm doing with the cameras on the rover as we drive along. And there's various levels. The innermost level is the highest resolution. We can see things in great detail. And then as we move out, the view is a little bit fuzzier, but you can still record some of the information. And meanwhile, while that's happening, remember, we have a ground penetrating radar, which is taking continuous stream of data about what's underneath us. So we could use that later to build up a cross section, which we field geologists like to do to kind of further understand what we're looking at with our maps. So this is just an example of one of those maps. So here are those 5 levels of mapping, and these little dots are where the rover stopped at various places. And so I've just mapped out certain things. We don't need to go into what all the colors are, but they're just different types of rock. But while we were sitting right here at this particular spot, we were able to examine these rocks out here in the distance, which were believed to be our volcanic rocks or lava flows that are capping all of these rocks that we landed on. They're sitting on top of it. And so we can actually see that. And so I wanted to show you a sense of what you can see from here and how you map it out. So here's a NavCam panorama. So here's some of those little polygon-shaped rock types that you saw in the previous image. And then way out here is that escarpment that I told you was our volcanic rocks. And so we have, remember, our Mastcam-Z has a telephoto lens, so we can zoom in and see those rocks up close. And so this looks for all the world like typical volcanic rock associated with lava flows here on the Earth. Very dense, a lot of gas bubbles or vesicles, as we geologists call them, and very vesicular, scoriaceous type rocks and so on. So that's just part of what we can see from the rover as we drive along. So since driving, I've kept track of the geology all along the way. So this is just a sample of some of that mapping along this traverse. And currently I'm working on filling it out as we go out to our current location. So getting back to just the pretty pictures. So on Sol 110, we passed by the rim of a small crater. Looking at it with Mastcam Z, you can see how much detail we have looking out in the distance with our high resolution cameras. And so we can get a understanding of what some of these rocks are. There's several different types of rocks in this scene, and everybody enjoyed picking all of these apart and arguing about them. But also there was a rock sitting out here that we imaged that was kind of interesting, that looks like it has these ropey textures that are very typical of young lava flows. It also has lots of those gas bubbles or vesicles, which is also typical of lava flows, obviously. And so we believe this is like a preserved sample of a Martian lava flow that was buried, and protected from erosion, and it was blasted out on the surface on the rim of this impact crater. Just an example of some of the fun things that we find along the way. So just another image along the drive on Sol 124. We were on the edge of this escarpment. Here's the escarpment out here in the NavCam panorama looking out. And here are some of those strange polygonal pattern rocks that we've seen ever since the landing site. And so a classic view, there's the rim of Jezero crater and the delta are on the right. And so we were headed to the south and we continued past. And if we could see well enough in this image, you could probably see the helicopter sitting out there, again, photo bombing this particular panorama. Looking further along, I thought this was interesting because it shows you what we can see from the rover. So here's Sol 136. We're sitting again on one of these strange polygonal pattern pavers. This is a Mastcam Z color enhanced image, so it's a little bit bluer and grayer. And it's looking out across the pavers or the polygonal rocks towards the outcrop over here. And here's the outcrop. And so you can see all sorts of things. For instance, this dark line here in the panoramic image is probably this one right here. This polygon or of rock here is likely this one, and so on and so forth. And there's all sorts of other geological details going on here. But basically, these rocks are sitting on top of this. And so this is our lava flows. This is whatever the heck these things are. And we'll talk more about those in a second. In fact, in this image, on Sol 127, we drove up and we decided our sampling instruments were ready to go. So we deployed our first attempt at sampling. And first thing we do is we abrade the surface of the rock. We have an abrasion tool. And we abraded a hole in our target rock here. And of course, it leaves behind a lot of dust. And on the Mars exploration rovers, Opportunity and Spirit, we had a brush that we would brush it off with. But on this rover, we actually used a little puff of gas to blow all the dust off. And here's a little movie showing the abraded hole with all its dust, and then we blow it off. And so you can see a fresh, clean, freshly ground rock face sitting there, ready to be investigated with Watson or microscopic imager and so on. And so doing so, then here's the view looking down, high resolution, the mapping of the individual rocks, and some of the blue lines of the fractures that are around it. The yellow is some of the little dunes and things. This is a 1 centimeter scale bar. This is what that braided spot looks like. You can see individual crystals. A little bit of debate about what all the crystals are. There's probably various minerals like pyroxene and feldspar and whatnot. And there's a lot of staining in here, probably weathering of iron minerals and so on. So we like the looks of this rock, so we decided we would go for a drill core, our first sample. So we selected a place just a little bit to the left from the rover's perspective of this particular abraded sample. And so we drilled a core there. And here's our coring tool in operation on Mars. You can see it rotating. This is the standoff pylons. Here's where the core goes into the surface. And inside is a core tube that is then basically deposited in the rover for safekeeping and eventual return to the Earth. So we drilled a core, and so here it is. And so this tremendous pile of tailings around the core. We looked inside, and sure enough, there's the missing rock, a lot of dust from the core, an awful lot of tailings from the drilling. Kind of a little suspicious about that, but the bottom line was we have a little camera that looks down into the core tube before we stash it away, and the sample tube was empty. So it was kind of a real mystery. What happened with it? Did it fall out while we were transferring it to the course collection tool on the front of the rover, or what? Some people, alien astronaut theorists who proposed that maybe aliens stole it. If you don't know, therefore aliens, right? But in reality, what we think happened was the rock is just simply rotten. That is, here's an example of a rock back near the landing site. That's the same rock type. And you can see that along the fractures, there's lots of weathering. So water probably, was percolating down through all the fractures, soaking the rock, doing all sorts of damage to it. And anybody who lives in the southeastern United States knows that there's a variety of rock called saprolite, or it's the rock that looks like, granite in the road cut. But when you walk up to it, it crumbles like sandstone. And it's simply rock that has been thoroughly, deeply weathered during some previous point in geologic history. And so we think that's what happened to these rocks, that they were deeply weathered and are now essentially rotten. The Latin word for that is sap, so this is sap rock, rotten rock. So the idea is that we need to find better rock to sample. We have an empty tube. We classified that as simply a Martian atmosphere sample with debris for the time being, and we've moved on. And while engineers were trying to figure out, what's the best course of recovery for our second attempt, we continued driving along our path because we're in a very time-constrained driving period. And so we continued driving from this location down here in the lower right, up along the escarpment to where we are today. And up until now, I haven't shown you anything about what the images from the RIMFAX, the ground penetrating radar, look like. But here's an example. So this is all the way from this location, Sol 169, to this location up here where we parked next to an outcrop up at Sol 173. And this is looking down into the ground 25 meters. And there's all sorts of details here. Here's a little blow up of this area here in the upper left. And you can, if you're a ground penetrating radar expert, you can make out all sorts of really interesting stuff going on with this. There's some sort of upper layer that's a couple of meters thick. It's a very low density. And then there's zones of higher density, and whatever it is, it's kind of tilted. So we, right away, we understand something about the structure of the deeper layers underneath the traverse. So we have this sort of data along the entire traverse. And so eventually, together with my field geologic mapping and this, we'll actually be able to kind of get a pretty good sense of what's going on here. But anyway, here we came up here and we parked up here, and I want to show you what we were driving along this escarpment. We started seeing our typical massive volcanic rocks on top in little patches now, very patchy. But along the side, there were these apparently layered or laminated rocks. And so we wanted to investigate those closely. And so we drove the rover up close to the outcrop here. And this is the image. So this is the outcrop. Here's our volcanic rocks on top. But here are the rocks. Again, they have that same sort of granular, sort of really deeply weathered look. lot of debate on the team about what these are. Many people think they're, sandstones or sediments from the distal edges of the delta. But others of us, including those of us associated with the ground penetrating radar, think that it's just more of the same rock that we just tried to sample. It's just now we're finally seeing it in cross section. And it has this kind of layered texture, which is also typical of, deeply eroded or weathered bedrock. So, and in this case, there's a little slump where this block has actually moved down. So you can actually map that out and kind of get a sense of what you're looking at. And so anyway, that's where we were just a couple of days ago. We just left that location and drove a little bit further northwest to the current location. It's almost Sol 180. It's coming up on the end of Sol 179. So in the meantime, the engineers decided what we're going to do is we're going to try another sampling attempt. Probably this coming week, probably beginning Tuesday, we're hopefully going to drive up on top of the escarpment and try to sample one of those dense volcanic or lava flow rocks on the top of the escarpment. And so that's coming up on Tuesday and probably for the next week or so after that. Once we finish, we'll continue to drive northwest along the escarpment and eventually then head into the interior of this Badlands, where we hope to investigate what these rocks are out here and try to understand the history before turning around and coming back. Here's where the helicopter is. It flew out across this terrain, so we have some images. They're just starting to come down now, and so we can get a sense of what we have in store for us. But that's what's coming up. So this is hopefully what Perseverance will look like in a couple of days from now as it samples. It makes its second sample attempt at the volcanic rocks on the escarpment. So that means when we're done, we'll continue back around and then arrive at the delta probably at the beginning of 2022. And so that's pretty much it for my presentation. I just wanted to remind you there is a book coming up this fall. It's called Missions to Mars, published by HarperCollins. And so if you enjoyed hearing about this mission or even previous Mars missions, you can read all about it in this book, as well as what we know about Mars. And with that, I'll stop and take questions.
Wow, that was amazing. I have a question while you guys are digging. I am actually doing a presentation in person at a nature center next month on Perseverance and Ingenuity. Where would be the best place? I mean, obviously I can't get your pictures, but what would be the best place for me to go to get the most current pictures and information?
NASA has a website, Mars 2020.
Okay,
and you can see images that, in theory, haven't been released yet. I mean, they're basically all of the images taken are available on that site, as well as the usual public release, nice, pretty well selected and explained images as well. So that's the place to go. You can also see the pathway of the rover along its traverse. Anything you want to know about Perseverance, including anything about the instruments and what the plans are.
They have videos there too?
And there are some videos in the public information site.
Okay, thank you so much.
You're welcome.
I have a question about deviations from mission. I assume that most of the route of the Perseverance lander is pre-planned, but how much latitude is there for deviation when you find things of interest?
Yeah, well, we've as we plan the proposed timeline for getting from one place to another, and if it's a big campaign like the one we're undertaking here, driving to the south, we plug into it a number of free sols or free days, where we can, if we have to, expend those to do something that we hadn't thought we would want to do. So for this particular drive, we actually plugged in, I don't know, 5 or 6 Martian days that we can actually drive off and look at something. In fact, we did that a couple of sols ago. But by and large, we like to stick to the plan, to keep on a timely arrival at our next location and make sure we accomplish all the mission goals. But we do build in these dead sols for both the fact that we might see something we want to investigate, and also because sometimes you just simply have a problem and the rover times out and we have to do it all over again the next day.
What are the terrain avoidance parameters for the mission? In other words, is there a certain pitch that you will not exceed, or?
Mm-hmm. Yeah, usually on Mars we can go up to slightly beyond 30-degree angle, and there are certain types of terrain like dust devil or dust dunes that we don't like to drive through. That's why we are avoiding the Badlands, because the traction can be kind of very limited in those locations, and you can easily get stuck. So we try to avoid those things, but by and large, we can drive over any rock up to and slightly larger than the diameter of the wheels, which are about 20 inches in diameter. We do have on board autonomous navigation skills. In fact, you just reminded me that I didn't mention on that one little image of Sol 124, that's where we initiated a thing called AutoNav, which is where the rover actually used the nav cams as it's driving along to actually select its own path. And that allows us to drive much, much faster and further on any given day. In fact, if you go back and look at those images of the traverse, after about Sol 124, the spacing between our stopping locations, the little dots along the traverse, are much, much further apart, typically 120 meters as opposed to 50 or 60 meters. So we're able to drive much further with AutoNav, and the rover drives, it's amazing to watch. It drives around a rock that just doesn't look good, and stays on path to the next location that we select for it, but it picks its way there. So it has basically what you would expect for a modern electric vehicle that can sense its environment and avoid hazards and obstacles.
And if I may ask one more, how do you protect the helicopter and your cameras in the case of a dust storm?
Yeah, in the case of a dust storm, the rover is pretty insensitive to dust storms. We've seen that with Curiosity during the global dust storm that basically brought Opportunity to its knees, because Opportunity was solar powered, and rovers are basically powered by a radioisotope thermal electric generator. The helicopter is powered by solar power, so if a dust storm came up, it wouldn't survive that, because it basically needs the sun to recharge the batteries, run heaters, and things like that.
Could it be tipped over, though, by the wind?
No, there's a lot of testing about that sort of thing, and the winds still do not exert enough force on the surface of Mars to even blow over the relatively lightweight helicopter.
Scott, any questions?
Yes, yes there are. Brian Lippincott from Facebook wants to know, is the RIMFAX the first ground penetration radar deployed on a Mars rover?
Yes, RIMFAX was the first ground penetrating radar deployed on a rover on Mars, and so it was quite a breakthrough to have that technology on board. And the interesting thing is, as the RIMFAX people have told me, it works much, much better than it does here on the Earth, because it's very sensitive to the presence of moisture. So typically on the Earth, we can go down just a couple of meters before things get kind of hazy because of the moisture. On Mars, we can penetrate apparently tens of meters now and still see the finest detail. So it's a beautiful place for ground penetrating radar. So hopefully we'll have ground penetrating radar on future missions and certainly along for the ride with any human exploration of the surface of Mars.
There's a question from Billy's Astro. Billy is watching from YouTube. He says, on the goals of the mission slide, is that an image of the rover on Mars or the test site on Earth?
Yeah, those are almost all of the images that weren't taken on Mars were just artist conceptions. So there's just high resolution artist drawings, like the one you're looking at now. Yeah, the rocks are extremely difficult for artists to do. And so they always look a little bit off. So that image of the rover in that slide showing the mission goals was showing potentially what was supposed to be, like the sediments in the delta. And of course, they looked a little bit more like, I don't know, slate rather than nice, finely bedded delta sediments. But yeah, that was just a drawing.
Andrew Corkhill, watching on YouTube, he didn't realize that they were going to retrieve samples from the rover. Can you talk a little bit more about the Martian retrieval mission?
Yeah, so the idea is to go down to the end of this decade. We'll be sending back a lander with a rover on the another mission, and the idea is that it'll be a rover that will basically follow the pathway of the rover to its sample cache sites on the surface. The rover will be tasked with collecting those samples, storing them on board, and returning them to the vehicle, which will send them to orbit, and they will return to Earth as a series of tubes, small tubes that you saw the scale of, finger-sized samples of Martian materials, very carefully documented as to where they were from and what type of rock they came from. And I don't know, that's pretty much the gist of the mission. The scope of the mission is pretty impressive when you actually look into what it takes to get down on the surface, find the samples, and return the samples to the Earth. They're completely sealed, so they're biologically protected for both forward contamination of Martian samples and back contamination of the Earth by any potential Martian microbes. And there's enough sample in those tubes for a variety of instrument laboratories here on the Earth, which have way more powerful instruments than we can send to the surface of Mars. And that's the concept. So we'll finally have real samples from the surface of another planet that we can actually say where they came from and what the history behind them was and analyze them in detail. And that'll be an explosion of geochemical investigation, much like the Apollo lunar samples were for the geochemical community here on the Earth when those samples are returned at the end of this decade.
We have Kelley. Oh, I'm sorry. I didn't mean to interrupt.
No, go ahead. Go ahead.
Can we have Kelley jump in with his question?
Sure.
Hey, Larry, great to see you again.
Hey.
Mars right now is about its farthest from Earth, like 2.6 AU or something on that order, which makes the round trip communication time sort of at their maximum. And yet, it seems to me these drilling operations are some of the most critical in the mission to date. How do you choreograph the drilling, and how often do you check in to, do tweaks and adjustments and such?
Yeah, well, it's like all rover missions thus far. We have two capabilities. One is sort of the standard way of operating is the rovers have a considerable amount of autonomy. We tell it what to do, and it knows how to do it. So there's that. So we tell it to drill this location, and it has a predefined sequence that it does to actually, put the drill on the surface, collect the sample, and then actually return it to the rover as a completed sample. And we tend not to interfere with that sort of process, but we do have direct to Earth communication, so that after the 20 or 30 minutes or so that it takes for signal to get back, we can, if necessary, intervene and do something else. We do that sometimes when there's some sort of emergency that we want to really get a handle on things, but by and large, it's pretty much once a day. We get a downlink, or maybe a couple of downlinks a day, and we communicate with the rover during those sessions, and it does what we tell it to do and sends back what it did, and we think about it, and the next day we tell it what to do tomorrow.
If I could just follow up quickly, how are the new tires holding up?
Yeah.
You have a little softer terrain here than Curiosity had.
Yeah, we upgraded the wheels from Curiosity. That was they made them a little bit too thin. We didn't really anticipate that driving over rocks on Mars, they can be quite sharp and uneroded, and so they were puncturing the beer can thin material of the treads. And so it's a little bit, they've been tested for not basically being damaged by little pebbles, the way the Curiosity wheels are. So they're a little bit tougher. They also have, slightly different tread pattern that's determined to be a little bit tougher and a little bit better for, operation on the surface of Mars. So yeah, you can bet those were thoroughly upgraded before we sent this rover.
There was a question about from Gregory Shanos, maybe Shanes. Why is the subsurface of Mars not reddish but gray?
Yeah, well, the deal is that most of the surface of Mars has a lot of dust on it, and the dust is kind of an orangish, reddish brown, and it coats everything. And if you brush that away, all too often, the surface underneath is much darker, and it's not quite as dusty. Of course, there are places where dust just is an integral part of the regolith or dirt, and it's still dusty, but the surface is bathed in just continual rain of dust that's very light, reddish brown in color, so it coats everything. Also, the extreme ultraviolet probably does some things to the sulfate minerals that are as components of the dust, and probably lightens them up. Because anytime you disturb the surface, you see a darker surface underneath. So Martian rocks are pretty much like Earth rocks. They're largely grayish to sort of a rusty grayish in color. It's just that the surface of Mars is coated with a very bright dust.
Great. And Ron Whitehead, watching from Facebook, asks, have they discovered meteorites, and are they of interest to investigate?
Yeah, on previous missions, we actually did see meteorites on the surface. We saw lots of those on both Spirit and Opportunity, and of course, Curiosity has seen some. And on this mission so far, we have not identified any. I'm sure we'll see some because they seem to be everywhere on the surface of the Mars as you're driving along. So I wouldn't be surprised if we eventually encounter some. With all that erosion, it's kind of like going into Antarctica, to collect meteorites. The ablation of the surface ice on Mars, leaves behind a collection of things that have fallen from the sky over the years. And so we anticipate seeing that here on the Mars. Just haven't seen it yet or identified it yet.
There's a question from Andrew Corkill. He says, hi, Larry. Is NASA sharing info with ESA and China as all this takes place? And is there a future collaboration in store?
Yeah, definitely. The sample return rover is already we're collaborating with ESA, European Space Agency, for that mission. So they're working on a rover. We'll probably have lots of input on the design of that, So that is in progress right now. So yeah, there is a collaboration. The Chinese are sort of operating independently. You can bet they're learning a lot from our missions. They tend to, well, we get the impression they reverse engineer a lot of things we've done. The Zhurong rover has many similarities with Spirit and Opportunity, right down to the calibration target for the panoramic camera. So I suspect they're learning a lot in that respect. As far as sharing the current activity, you hear about as much about what's going on with the Chinese rover as we do. So there isn't a lot of communication between the two countries in that regard. So it's kind of like the old Soviet era, when we really didn't communicate with the Russians. That's what's going on right now with the Chinese. We hear it when you do.
And Raymond Bradley asks, can you speak to the current research on the origin of methane in the Martian atmosphere?
Yeah, well, there's still, it's pretty much probably, if you've read anything about it, you've probably read all that we know about it thus far. The European mission that's currently orbiting Mars was sent specifically to find methane and its currents, its locations, concentrations, and so on. And so far, they have not seen any, which is curious because at the same time, Curiosity was encountering brief encounters with some methane on the surface of Mars. So, there's two possible origins for methane. One is inorganic, because there's a process in geology where you take precisely these types of rocks that we're seeing, the volcanic rocks, the dark basaltic volcanic rocks, and you expose them to carbon dioxide and lots of water, and especially in the deep substrate. And you basically break that down, you turn it into a thing called serpentinite, and release a lot of methane and stuff like that. So that's a good source on Mars. We know there's lots of the materials for making methane. Of course, the other is the idea that it's somehow microbial. Whatever the process of injection in the atmosphere is, it has to be fairly frequent, and because methane doesn't last in the atmosphere very long, it goes away very quickly. So to see it at all means that it was just produced or released into the atmosphere. So that's also entirely possible with inorganic as well as organic. As you can imagine, organic, some microbes burp someplace and we end up with methane. But also with inorganic, periodically you get releases of gas from the deep interior of any planet. Even here on the Earth, we're starting to recognize that deep gases from the mantle are actually released, especially in concentrations in areas where there's lots of faulting or other conduits up from depth. And it is especially common in places where there's less water to kind of contaminate and flush the substrate of gases. So it's right now the thinking is that it could be both, but many of us, if we had to place our bets, we would bet on the inorganic because we know we have all the conditions for that. And it's simply released periodically in locations, and so you won't see it very often or in very high concentrations unless you happen to be looking in the right spot.
Let's make that the last question. We probably need to get back. Dr. Crumpler, thank you so much. This has been amazing.
You're welcome.
Really appreciate it. A great talk, just fascinating.
Okay.
Thank you.
We have one person who says we should bring you back every week to give us updates. We won't pester you.
Please don't.
We'll take weekly reports. Thank you so much.
You're welcome. Thank you.
Sure. All right, Chuck, you ready to do some door prizes?
I think so. And our next one is contributed by you, Terry.
Okay.
You have contributed a $250 Explore Scientific gift card. And I will share screen and do the random number generator. And the number is 230.
230. Okay. You couldn't just pick one between 1 and 50, huh?
Sorry.
My first page. Okay, but it's not going to take long. 2:30. Mike Wiesner.
Mike Wiesner. Okay, congratulations, Mike. Got some equipment to buy.
Yes.
Okay. Now, may I ask, is there thank you, Terry. Very
Sure.
generous. And is there someone here from the Houston Astronomical Society?
I am here. This is Joe Califf, president
Joe,
of
yes.
HAS.
I didn't see you. I'm sorry, Joe. How are
No
you?
problem. I was off of video.
Okay, we're going to draw. You have 2 door prizes. Is
We
that
do.
correct?
We wanted to really participate in this door prize efforts here. So absolutely. We've got a Fujinon Mariner 7x50 binoculars, as well as Nikon Action EX 10x50 CF binoculars as
Wow.
well. So
Which one are we giving away first?
let's give away the Nikons first. Let's do that.
The Nikons first. Okay. And I'm going to draw a number first. Actually, I'm going to draw 2 numbers for both of them, and then we'll let you talk about your club for a moment. That'd
Certainly.
be okay? All right.
Absolutely.
All right. Terry, the first number is 775.
Okay.
And the second number is 388.
All right.
All
Okay,
right.
thank you.
And I will stop sharing. And Joe, tell us about the Houston Astronomical Society, please.
Wonderful. Absolutely. And let me know, starting the share now, let me know if you can see my desktop there.
Looks great.
Okay, perfect. Well, I just flew in from Hawaii, so I apologize for sounding a little tired. But first, I'd like to congratulate Terry, Chuck, Carol, everybody else at the Astronomical League for hosting a wonderful ALCon virtual this year. As somebody who contributed in a small way to the planning and hosting of the virtual Texas Star Party online this year, I know firsthand how much time and effort goes into putting these events together. And by all accounts, this is a wildly successful ALCon. It's great to be back together with our friends in the astronomical community, even if it's just virtual right now. And we hope that next year allows us an opportunity to get together in person. So we at the Houston Astronomical Society are excited to participate in and support ALCon Virtual. Our club has been a longtime member of the Astronomical League, and I can't tout the benefits of the AL to our members enough. Our club is one of the oldest astronomy clubs in the great state of Texas, and certainly one of the largest in the United States. With over 870 members at the end of last year, we continue to serve those interested in astronomy through the execution of our mission statement, which is to foster the science and art of astronomy through programs that serve our membership and our community. And through those programs, you'll find much influence from the Astronomical League itself. So as I mentioned before, our club has been around for a little while, having been founded in 1955. Our first president, Woody Myers, had a truck-mounted 25-inch Cassegrain telescope that he'd travel around town with to share views of the night sky with other Houstonians. So you can see that outreach is in our DNA here in Space City. We have a wonderful private observatory and dark site for our members nestled in 18 acres. That's approximately 80 miles west of the Light Dome of Houston. We also have a very popular and active outreach group that pre-COVID performed about 3 events per week. Some of those were as small as visiting a preschool to show telescopes to a group of 5-year-old kids. And I believe the largest that we did was an electronic dance music festival that had over 60,000 attendees over a 3-day long weekend. Additionally, we have an extensive loaner telescope library for members to borrow from. At last count, I believe we had 44 telescopes and an assortment of binoculars and other tools for club members to use as a benefit of membership. But our most valuable asset, and I can't preach this enough, is our members, many of whom have made significant contributions to astronomy. This includes Ed Sapansky's comet, his eponymous comet, Comet Sapansky. You can see it as a little blur there. There's a better image of it. Larry Mitchell's supernova, 1994S in NGC 4495. Barbara Wilson, the late Barbara Wilson, who had many contributions, including the data of this collaboration published by the American Astronomical Society regarding the globular cluster IC 1257 in the galactic halo. Brian Kudnick, who was the first person actually to have a confirmed visual observation of a lunar meteor impact. And Jay McNeil, an astrophotographer who, while doing some astrophotography in the Orion region, discovered what's known as McNeil's Variable Nebula. So you can see there at the top and at the bottom the difference in those pictures. And we have lots of members who contribute to astronomy in what we call pro-am research at our observatory and on their own. And lastly, I just wanted to mention that our wonderful outreach volunteers are going to be honored aboard the International Space Station when Boeing's OFT-2 mission finally launches. It was supposed to launch, I believe, 2 weeks ago, and that's been pushed back a little bit. But one of the contractors on this mission wanted to acknowledge all of the work that HAS volunteers have been doing, and a number of our club branded items will be flying aboard OFT-2. One of these items is a USB stick with a slideshow of our outreach efforts. We were told would be broadcast from the International Space Station as a tribute to us for, quote, inspiring the next generation of STEM leaders and space pioneers. So I thought I'd mention that so that others might watch that when OFT-2 does finally launch. And so I wanted to get through that as quickly as possible and say that's a little bit about us. And thank you very much for allowing us to speak with the rest of the folks that are on this program today.
That is just incredibly impressive. Just amazing. And I wanted to ask you a question. I understood that Jay McNeil did he used to live in Paducah, Kentucky, and now is he now in Texas?
I believe he was in Texas and now is in Paducah, Kentucky.
Oh, okay. Just wanted to be sure. Okay, thank you.
Absolutely.
Okay. If we could have you stop sharing.
Certainly, let me do that now.
And have you hold up, first of all, the Nikons. And Terry will tell us who will get them.
The winner of the Nikon binoculars is Bruce Pollard.
Okay, congratulations, Bruce. A nice set of binoculars coming. And the other binoculars, the Fujinons?
And the Fujinons is D. Friesen.
Excellent. That will help in his recovery. He's having some medical issues, and I know you'll be greatly appreciative. Thank you so much, Joe, for being here. I know you had to travel back from Hawaii yesterday, and your schedule has got to be as messed up as after an all-nighter observing. So,
well, I wanted to make sure I was here for this, so this was my top priority. So thank you very much, Chuck, Terry, and everybody else for including us.
Thank you.
Thank you so much.
Thank you.
Do we have anyone here from the New Hampshire Astronomical Society? Wyatt Davis or anyone else? Okay, we're going to go ahead and draw for this. I don't have anything from them. Let me double check just to make sure. Okay. Give me 1 second.
Sure.
Some clubs have sent in materials to show, and I don't have that, but if they appear later and I may communicate with them later, we'll give them an opportunity to talk about their club.
Okay.
So they have offered a $200 High Point gift certificate, and I'll go ahead and we'll draw for that now.
Okay.
Oops. Okay, and the number is number 26. That should help you.
26. Yes, it will. 26 is Steve Borner.
Steve Borner. Congratulations, Steve. And to the folks in New Hampshire, thank you very much. And again, if you're listening, we can certainly give you an opportunity to talk about your club in the next session. And we're going to take a break now, and we'll be back with Kelley, Beatty, and some other excellent door prizes at 8 o'clock tonight.
See you then.
Time.